Anypoint integration platform in MuleSoft. Now we are focusing on Anypoint integration platform. The MuleSoft's Anypoint platform is a unified single solution for IPaaS and a full lifecycle API management. The Anypoint platform consists of the following major components: Anypoint Security, Anypoint Design Center, Anypoint Management Center, Anypoint Exchange, Runtime Engine and Services, API-led connectivity, Application Network, Data View. Cloud Hub 2.0 is a fully managed, containerized integration platform as a service PaaS, where you can deploy APIs and integrations as lightweight containers in the cloud. Mule, the runtime engine of Anypoint platform, is a lightweight Java-based enterprise service bus ESB and integration platform that allows developers to connect applications together quickly and easily, enabling them to exchange data. It enables easy integration of existing systems regardless of the different technologies that the application use, including JMS, web services, JDBC, HTTP and more. The ESB can be deployed anywhere, can integrate and orchestrate events in real time or in batch, and has universal connectivity. Here you can see critical components of MuleSoft Anypoint platform. Anypoint MuleSoft Management Center, a unified web interface to efficiently manage all critical aspects of the platform, including but not limited to traffic, service level agreements, SLAs, API users, underlying integration flows, and more. Anypoint connectors offers state of the art tools and assets you need to connect faster. Anypoint Design Center, development tools that make it quick and simple to implement integration flows, design APIs, and build connectors. Anypoint Exchange, a collaboration hub to search for private, pre-built and public reusable assets. Runtime services, an extensive suite of platform services that offer enterprise-grade scalability, security, high availability and reliability. Mule Runtime Engine combines real-time orchestration and application integration with robust data integration capabilities. Here you can see Anypoint Design Center. Within that you can see Studio, API Designer, Connector, Div Kit. And here you can see Anypoint Management Center. Within that you can see Runtime Manager, API Manager and Analytics. Between you can see Anypoint Exchange. Below Anypoint Design Center, Anypoint Exchange and Anypoint Management, you can see runtime services and Mule runtime engine. Below Mule runtime engine, you can see there's Anypoint connectors, and below runtime engine, hybrid cloud is there. This diagram illustrates the relationship between design tools and other MuleSoft products. Anypoint Design Center includes a web-based tool where MuleSoft developers design and create API specifications and fragments. API designer. Once your API specification or fragment is ready to be shared with the rest of the organization, you publish it to Anypoint Exchange for testing and approval. This development approach is spec driven. Before moving into API implementation phase, it's crucial to get the sign off from the business and other teams involved. They will test the API returning mock results, provide initial feedback and validate requirements. Anypoint Exchange is a virtual market to share, discover and reuse APIs, connectors, templates, etc. Other part of the design center, Flow Designer, is used to build Mule applications that connect systems into workflows. Here, specification writer uses API designer. The design center consists API designer and flow designer. Anypoint platform consists of design center and Anypoint Exchange and API manager. Developer uses Anypoint Studio. Anypoint Studio imports API specification as connectors for Mule apps from API designer. And API Studio imports API specification as connectors for Mule apps from Anypoint Exchange. API designer publishes specification and fragments to and imports them from Anypoint Exchange. Anypoint designer can create dependencies on assets in Anypoint Exchange. Citizen designer uses Flow Designer. Flow Designer imports API specification as connectors into Mule apps from Anypoint Exchange. Developer uses API Manager. API Manager imports API specifications from Anypoint Exchange. Here you can see a Cloud Hub 2.0 architecture. To understand Cloud Hub 2.0 security and availability, you should understand the architecture behind Cloud Hub 2.0. Cloud Hub 2.0 architecture comprises two major components: Anypoint Platform Services and shared global regions. These two components, along with Anypoint Runtime Manager, through which you can access them, work together to run your integration applications. Integration applications that you create and deploy to Cloud Hub 2.0 to perform integration logic for your business. Runtime Manager, user interface that enables you to deploy and monitor integrations and configure your account. platform services, shared Cloud Hub 2.0 platform services and APIs, which include Anypoint monitoring, alerting, logging, account management, private spaces, secure data gateway, and load balancing. Cloud Hub 2.0, an elastic cloud of replicas, an elastic cloud of replicas, instances that run integration applications. Here, integration applications. An integration application is any integration that you have built using Anypoint Studio. These applications can do everything from synchronizing data from Salesforce to a database, to publishing a SOAP or REST API, to creating complex orchestration of business processes. Platform services. Platform services are responsible for coordinating all aspects of the platform. They coordinate deployment of applications, monitor integrations, provide analytics data, store application data, run schedule jobs, and more. Many of these services are exposed through the Cloud Hub 2.0 REST API. Cloud Hub 2.0 replicas. Replicas are dedicated instances of Mule runtime engine that run your integration applications on Cloud Hub 2.0. Replicas have following characteristics. Capacity. Each replica has a specific amount of capacity to process data. Select the size of your replicas when configuring an application. Isolation. Each replica runs in a separate container from every other applications. Manageability. Each replica is deployed and monitored independently. Locality. Each replica runs in a specific global region, such as the US, EU, or Asia Pacific. The memory capacity and processing power of replica depends on how you configure it at the application level. Replica sizes have different compute, memory, and storage capacities. You can scale replicas verticality by selecting one of the variables vCore sizes. Replicas within fewer than one vCore provide limited CPU and I/O apps with similar workloads, can burst to higher CPU speed for short time. This ability helps to improve application startup times and to process infrequent large workloads. Note that application bursting depends on resource availability for nodes and is not guaranteed to occur. If you need consistent performance, use replicas with more vCores. Replica with one or more vCores provide performance consistency. Each replica has a minimum 8 GB storage, which is used for both system and application storage. If your application requires more storage, for example, verbose logging, use a replica with 2 or more vCores, enabling the application to access additional storage in /temp. All applications, including stopped applications, count toward replica usage. To prevent stop application from consuming resources, delete the application. If your applications require more vCores than are available, Cloud Hub 2.0 allows you to create an application, but you cannot start it until the additional vCores become available. To increase vCore allocation, delete an application or contact your account manager. To increase your subscriptions vCore allocation. Note applications that are stopped till consume vCores as if they were running. The metaspace limit for apps deployed to Cloud Hub 2.0 is currently 256 MB regardless of the replica size. The initial metaspace size is 128 MB. Metaspace garbage collection begins after the metaspace reaches that threshold. You can scale your applications horizontally by adding multiple replicas for persistent queues. Cloud Hub 2.0 monitors replicas to verify that they are operating correctly. If you enable automatic restart, Cloud Hub 2.0 also automatically restart application if necessary. Shared global regions. Cloud Hub 2.0 provides ability to deploy apps in different regions of the world: North America, South America, the European Union, and Asia Pacific. This global distribution enables you to host your integration in the local closest to your services, thus reducing latency. It can also provide for adherence to local laws such as the EU Data Protection Directive for the US Cloud and MuleSoft government cloud control planes. MuleSoft hosts the management console and platform services in the United States. For EU cloud control plane, MuleSoft hosts these services in Europe. The region that you deploy your application to determine the domain provided by your application. Load balancer that Cloud 2.0 uses to route request beside in the same region as your application. Here, integration apps are connected to Cloud Hub 2.0. Runtime Manager interacts with platform services. Platform services consist REST API, Object Store version 2, Anypoint monitoring, logs, alerts, private specs, replica management, and schedule management. Platform services interacts with Cloud Hub 2.0. Here you can see the graphic. The graphic shows this graphic shows the dedicated Anypoint VPC architecture. An Anypoint VPC is a logically private and isolated network hosted inside the Cloud Hub. You can connect to a private intranet to your Anypoint VPC as if they were all part of a single private network. The Anypoint VPC configuration exposes the DNS record, mule worker internal app name cloudhub.io. This is a DNS A record which includes the IP address of all of your workers, IP addresses of all of your workers. This DNS record cannot be accessed from outside your Anypoint VPC. Each Anypoint VPC allows you to configure firewall rules to check inbound connections directly to your workers. Four firewall rules are created by default. 2 rules that allow your private address space to connect through ports 8091 and 8092, and two rules that allow external request proxies by Cloud Hub, shared load Cloud Hub's shared load balancer, through ports 8081 and 8082. All traffics that is not allowed in a firewall rule is blocked by default. Here external intranet interacts with DNS record in VPC. IPsec tunnel VPC peering direct connect is passed back and forth between DNS record and intranet. Here worker app names, workers and firewall rules and DNS records are inside VPC. DNS record is connected to firewall rules and firewall rules are connected to workers here. Here public internet is connected to DNS record in shared load balancer. In the Cloud Hub you can see shared load balancer and DNS record and VPC. This DNS record is inside shared load balancer and shared load balancer is connected to DNS record here. 8081, 80 HTTP and 82 443 HTTPS pass from shared load balancer to DNS record here, and DNS record here is connected to firewall rules here, and this public internet interacts with DNS record here also. Here this graphic shows the Anypoint VPC architecture with a dedicated load balancer. You can configure a dedicated load balancer inside your VPC, which allows you to provide custom certificates and optionally enforce two-way SSL client authentication. If you configure proxy rules that map your applications to custom domains, you can, for example, host everything under single vanity domain. A Cloud Hub dedicated load balancer is assigned to a particular Anypoint VPC. A dedicated load balancer then routes traffic to a particular Anypoint VPC within a particular service region of the VPC. Each dedicated load balancer has a DNS A record. It's a IB name it's a LB name dot LB dot anypoints DNS dot net or lb dash name dot l dash lb dash prod dash eu dash rt dot anypoint dns dot net for EU control panel that resolve to two public IP addresses of its two instances. Throughout your DNS provider, you can add CNAME record pointing to the dedicated A record and use your own domain names to access it. This DNS A record can also be reached from outside VPC additionally. Outside VPC. Additionally, a Cloud Hub dedicated load balancer has an internal domain name to be used by applications and clients within Anypoint VPC. The structure is internal dash lb dash name dot lb dot anypoint dns dot net. Here you can see public internet is connected to SSL endpoint and DNS record and SSL endpoint and other internal DNS. This DNS records are inside dedicated load balancer. Intranet interacts with DNS record here, starting with internal dash lb dash name, and IPsec tunnel VPC peering direct connect is passing back and forth to and from intranet and DNS record. Two-way TLS is passed to and from DNS record to SSL endpoint. Dedicated load balancer and mapping rules, DNS record here, and firewall and workers are inside VPC. Dedicated load balancer is connected to mapping rules. Mapping rules are connected to DNS record here, and 88, 8091, 80 HTTP and 8092 443 HTTPS are passed from mapping rules to DNS record. This DNS record is connected to firewall rules, and firewall rules are connected to workers here. And in the Cloud Hub, you can see shared load balancer with and DNS record and VPC. This DNS records here in shared load balancer, and 8081, 80 HTTP, 8082, 443 HTTPS are connected to DNS record here. Here you can see a Mule ESB. The key advantage of an ESB is that it allows different applications to communicate with each other by acting as a transit system for carrying data between applications within your enterprise or across in the internet. Mule has powerful capabilities that include service creation and hosting. Expose your host reusable services using the ESB as a lightweight service container. Next point, service mediation. Shield services from message formats and protocols. Separate business logic from messaging, and enable location independent service calls. Next point is message routing. Route, filter, aggregate, and resequence messages based on content and rules. Next point is data transformation. Exchange data across varying formats and transport protocols. Here, business applications, portals. Here the Mule transporters and connectors are connected to business applications, portals, rich clients, trading partners, B2B, data resources, and connectivity services, adapters. Mule transports or connectors are connected to Mule integration services, routing, transaction management, transformation, message broker, transportation management, and security are inside Mule integration services. Below Mule integration services, app container is there. It's optional, and with app container you can see Tomcat, WebLogic, WebSphere, JBoss, JTO, Geromino is there. Here you can see the architecture of Mule Management Console. Mule Management Console MMC was deprecated in December 2015. Its end of life is July 2015-2019. This diagram summarizes the architecture of the Mule Management Console. Here, the Mule ESB instances monitored by MMC. This can be standalone or embedded instances or clusters. To here the MMC agent contained in the Mule instance, which is responsible for facilitating data transfer between the Mule instance and MMC. applying changes, that is thread pools and configuration file changes to the Mule applications. The number 3, the Mule instance, the MMC instance. The MMC instance, the web-based interface that interact with Mule through MMC agent, JMX function, and next point is JMX functionality exposed by Mule. MMC instance is a web application package as MMC instance is a web application package as a WAR file that execute from within your web servlet container, that is Tomcat, JBoss, etc. Number 4 here, transactional database, that is stored business event transactional data collected by the MMC agent within the Mule instance. This database by default is an H2 database, but you can configure MMC to use other relational databases. Number 5, the environmental database, that is stores state information about various Mule instances and applications managed by MMC, including alerts, deployments, configuration, etc. The database is by default Apache Jackrabbit, but you can configure MMC to use other relational databases. Number 6, MMC's REST interface, which exposes MMC functionality through a REST API. MMC users can invoke this API to apply MMC users can invoke this API to programmatically Mule instances paired with MMC. Here you can see Mule ESB instances, and you can see MMC agent here within Mule ESB instance. This instance interact, and MMC agent interacts with the MMC web application, the console. MMC web application, the console, is connected to transaction data, business events, environment data. This MMC application, the console, is connected to console interacts with MMC REST API here. Component lifecycle. This is related to developing components. When developing components, you focus on developing code to handle the business logic, not to integrate the component with Mule. For example, if you are developing a component that adds customer data to an invoice, you focus on writing code that queries the customer database and updates the invoice as needed. You do not have to write any special code to handle the message that's passed to the component or to integrate with Mule, as all integration is handled through configuration. You can develop the component as a POJO or as a web service using popular container such as Spring, EJB, or Plexus. Component lifecycle. Your component can implement several lifecycle interfaces. The lifecycle flow typically look like this, with the on-call often being replaced by an entry point resolver. Following are the most commonly used lifecycle interfaces: org.mule.api.lifecycle.initializable. This is called only once for the lifecycle of the component. It is called when the component is created and when the component pool initializes. With the interface initializable, the initializable is a lifecycle interface that gets called at the initialize lifecycle stage of the implementing service. Here you can see the method initialize. The method is used to perform any initialization work. If a fatal error occurs during initialization, an initialization exception should be thrown, causing the Mule instance to shut down. If the error is recoverable, say by retrying to connect, a recoverable exception should be thrown. There is no guarantee that by throwing a recoverable exception that the Mule instance will not shut down. org.mule.api.lifecycle.startable. This is called when the component is started. This happens once when the service starts and whenever the component is stopped and started either through the API or JMX. The interface startable provides an object with the start method which gets called when the Mule instance gets started. This is mostly used by infrastructure components, but can also be implemented by service objects. This lifecycle interface should always be implemented with its opposite lifecycle interface stoppable. And here you can see the method start. Here you can see the interface org.mule.api.lifecycle.callable. Callable is used to provide service with an interface that supports the event calls. Components do not have to implement this interface. Through the on-call method provides an example lifecycle method that is executed when the event is received for the implementing service. Here you can see on-call method passes the event to the listener. And here you can see org.mule.api.lifecycle.stoppable. This is called when the component is stopped. This happens when the server stops. So whenever the component is stopped, either through the API or JMX. With the interface stoppable is a lifecycle interface that introduces a stop method to an object. This lifecycle interface should always be implemented with its opposite lifecycle interface startable. org.mule.api.lifecycle.disposable. This is called when the component is disposed. This is called once the server shuts down. And with the interface disposable is a lifecycle interface that gets called at the disposed lifecycle stage of the implementing service as a service is being destroyed. You can see the dispose method here, a lifecycle method where implementer should free up any resources. If an exception is thrown, it should just be logged and processing should continue. This method should not throw runtime exceptions. And here you can see default constructor is connected to initialize is connected to start is connected to on-call is connected to stop is connected to dispose methods. Here you can see Anypoint virtual private network in Cloud Hub 2.0. Anypoint VPN virtual private network creates a secure connection between your private space and your on-premises network. Anypoint VPN enables apps running in the private space to access the resources on your on-premises data centers behind your corporate firewall. You can create multiple site-to-site VPNs if required. If the number of VPNs you can create depends on the network connection entitlements available on your account. Contact your MuleSoft account representative if you don't know how many network connection entitlements you have on your account. Anypoint VPN supports site-to-site Internet Protocol Security (IPsec) connections between the private space and the VPN endpoint. The gateway device is a physical or software compliance located in your network. MuleSoft side of the connection is an implementation of a virtual private gateway. VGW. The MuleSoft VGW is associated with a single private space but can support up to 10 VPN connections. To create an Anypoint VPN connection to your network, create a connection to your external network in the documentation. Here you can see a private space. You can see the private space in Cloud Hub 2.0. Here the private space 10.0.0.0/24, and here Cloud Hub interacts with the Cloud Hub external gateway IP address here. Here in this example 54.208.209.9, and it interacts with the Cloud Hub external gateway IP address interacts with the your external gateway IP address via IPsec and tunnel is 217.18.13.66. Here the data centers are in on-premises data center. Here the 192.168.177.0/24 here. Here you can see here you can see configure high availability with Anypoint VPN. Following example here, this shows a high availability VPN topology using a single Anypoint VPC and two VPN connections. MuleSoft virtual private gateway VGW supports one Anypoint PVC association, but it supports up to 10 VPN connections. You can locate your VPN gateway in the same data center or different physical connections. The BGP routing to advertise the same route via VPN 1 and VPN 2. In this scenario, the VPN gateways are configured to prefer VPN 1 tunnel, VPN 1 tunnel 1, VPN 1 tunnel 2, then VPN 2 tunnel 1, and finally VPN 2 tunnel 2. This configuration produces an automatic failover to another tunnel and to another VPN in the event of VPN connectivity issue. This makes the Anypoint VPN solution more resilient and robust. High availability VPN connections also support static routing, in which you establish a VPN 2 to work as a redundant standby connection in the event of failure with VPN 1. Here you can see private space. Here applications are in private space, and private space is in Cloud Hub 2.0. It's in here the it interacts with the MuleSoft virtual private gateway. Here Anypoint VPN 1 is connected to MuleSoft virtual private gateway via tunnel 1 and tunnel 2, and here the Anypoint VPN 2 is connected to MuleSoft virtual private gateway via tunnel 1 and tunnel 2. Here Anypoint VPN is connected to customer VPN gateway, and here the Anypoint VPN 2 is connected to customer VPN gateway. Customer VPN gateway is interested with the customer network here. Here you can see transit gateway attachments. The AWS transit gateway acts as a cloud router in AWS, simplify network access between private spaces, on-premises data centers, and third-party software, while providing increased visibility and control over the network. Transit gateways effectively merge your organization cloud resources and the on-premises data centers into one network topology. On Cloud 2.0, you can take advantage of this network's implication by securely attaching your private space to AWS transit gateway in your AWS account. You can add multiple transit gateways to your endpoint platform organization. The number of transit gateways you can add depends on the network connection entitlements available on your account. Contact your MuleSoft account representative if you don't know how many entitlements are associated with your account. To use the transit gateway attachment, your private space and AWS transit gateway must be in the same region. Here you can see private space. Here the 10.0.0.0/24 is in Cloud Hub 2.0. Here the private space interacts with the transit gateway via VPC attachment. Here the Cloud Hub 2.0 transit gateway and AWS VPC are in AWS region. Here the transit gateway interacts with private space via VPC attachment, and AWS VPC via VPC attachment, and on-premises data center via VPN. Here the with the data centers are in the AWS VPC here, and the on-premises data centers are in the on-premises data center here, and here you can see the firewall. Here you can see Cloud Hub 2.0 at architecture. To understand the Cloud Hub 2.0 security and availability, you should understand the architecture behind the Cloud Hub 2.0. Cloud Hub 2.0 architecture comprises two major components: Anypoint platform service and shared global regions. These two components, along with the shared global regions, and these two components, along with Anypoint runtime manager, through which you can access them, work together to run your integration applications. Here the one integration applications that you create and deploy to Cloud Hub 2.0 to perform integration logic for your business. Here runtime manager, user interface that enables you to deploy and monitor integrations and configure your account. Here the shared Cloud Hub 2.0 platform services and API, which include Anypoint monitoring, alerting, logging, account management, private spaces or secure data gateway, and load balancing. Here the platform services are here. The shared cloud 2.0 platform services and APIs, which include Anypoint monitoring, alerting, logging, account management, private spaces, so secure data gateway, and load balancing. Here the Cloud Hub 2.0, an elastic cloud of replicas, Mule instances that run integration applications. Note, you can view the live status and detailed service history for Runtime Manager, Platform Services, and Cloud Hub 2.0 on status.mulesoft.com for default US hosted control plane, and EU1-status.mulesoft.com for EU control plane. Integration applications. An integration application is any integration that you have built using Anypoint Studio. This application can do everything from the synchronizing data from the Salesforce to the database, to publish a SOAP or REST API, to creating complex orchestrations of business process. Runtime Manager. Runtime Manager is integrated into Anypoint platform. Sign in with your Anypoint platform credentials to deploy them and manage integration application at runtime. Console provides the monitoring information from the platform services, and also functions as a comprehensive dashboard for both application level and account level management. Administrator account holders can use the Anypoint platform to add and manage other users in the organization, define user roles, create and manage sandbox environment. Platform services are responsible for coordinating all aspects of the platform. They coordinate deployment of application, monitor integrations, provide analytics data, store application data, run schedules jobs, and more. Many of these services are also exposed through the Cloud Hub 2.0 REST API. Here you can see application integration apps are connected to Cloud Hub 2.0. Cloud Hub 2.0 interacts with the platform services, REST API, Object Store version 2, Anypoint monitoring, logs, alerts, private spaces, replica management, and schedule management are in platform services. Platform services interacts with the runtime manager. Here you can see Cloud Hub components, load balancer, virtual private cloud, and a DNS record of the Mule workers. The Cloud Hub provides a variety of tools to architect your integrations and APIs, so they can the Mule workers. The Cloud Hub provides a variety of tools to architect your integrations and APIs so that they are maintainable, secure, and scalable. Here you can see the basic network architecture, DNS, and firewall rules. This image shows the Cloud Hub components, load balancer, virtual private cloud, and DNS record of the Mule workers. Load balancing. Cloud Hub provides the load balancing service for all integrations. You can use the default balancing service to obtain dedicated load balancer. Cloud Hub load balancing service does round-robin load distribution across workers, which allows workers to scale linearly as they receive more requests. Load balancing service also provides transparent switch holder when an application is upgraded. Each application deployed on the Cloud Hub has a CNAME record that refers to the load balancer. For example, myapp.region.cloudhub.io Mule application deployed to the Cloud Hub must listen to the host 0.0.0.0 and to either HTTP port 881 or to the HTTPS port 882. Following ports are assigned to the mule worker. HTTP port is set to 881. HTTPS port is set to 882. The load balancer then forward requests to the assigned ports on the mule worker. Forward traffic still uses HTTP and HTTPS protocols, which means it can't listen to the HTTPS on $sign open curly brace HTTP dot port close curly brace or plain HTTP on the HTTPS dot port. You must reference these ports using the reserved properties HTTP dot port and HTTPS dot port recursively. Cloud Hub services can then dynamically allocate a port at deployment time. DNS records the following DNS records for your applications are exposed when they are deployed to Cloud Hub. myapp.region.cloudhub.io, load balancer port 80 and 443 forward to HTTP dot port and HTTPS dot port respectively. Mule worker myapp.region.cloudhub.io, the external IP address of the mule worker. Public HTTP services are exposed on HTTP dot port and HTTPS dot port. Mule worker internal myapp.region.cloudhub.io, the internal IP address of the mule worker, the IP address for this DNS record are accessible only within a customer's private Anypoint VPC. These IP addresses are not accessible for workers running in the MuleSoft shared VPC. Internal HTTP services are exposed to http.private.port and https.private.port. The default assigned ports are 91 and 892 respectively and cannot be changed. In certain situations, you may want to know the application's internal IP addresses. For example, when communicating with worker directly within the customer Anypoint VPC without sending data over the public internet. When setting up your own load balancer, you can access these IP addresses through the mule worker internal myapp.region.cloudhub.io record within the Anypoint VPC. If you access the workers directly, any load distribution benefits from the Cloud Hub load balancing layer are lost. Here you can see load balance is connected to myapp worker 1 and myapp worker 2. myapp worker 1 and myapp worker 2 is in optional VPC, and optional VPC interacts with the external VPC network. Here we are considering building Mule applications to support persistent queues. In Cloud Hub. For your application to benefit from the persistent queuing, implement the reliability patterns in your application code, separating individual XA transactions. The reliable acquisition flow reliably delivers a message from an inbound HTTP connector to an outbound VM endpoint. If the reliable acquisition flow cannot put the message into the VM queue, it ensures that the message is not lost by returning the unsuccessful response to the client, so that the client can retry the request. Application logic flow delivers the message from the inbound VM endpoint to the business logic processing in your application. This flow represents one transaction. Your business logic may involve several other transactions not shown. Between these two flows, VM queues hold the messages committed by the reliable acquisition flow until they are ready for processing by the application logic flow. In case of processing error within a transaction, or in the case of transaction timeout, that the allotted for the transaction is exceeded, Mule triggers the rollback. This rollback erases any partial processing that has occurred in the message and passes the message back to the queue. If your Mule instance experiences an outage and is unable to execute rollback transaction automatically roll back once the time allotted for the transaction is exceeded. Allotted time is determined by the timeout attribute of the transaction element. You can configure timeout yourself or accept the default. It is helpful to think that each transaction in terms of 3 steps. Begin. Mule kicks off the processing of all subcomponents within the transaction. Commit. Mule send the result to the completed transaction to the next step. For XA transaction, commit step has 2 phases: commit request phase and commit phase. During the commit phase, Mule coordinates the result of the Mule resources within the scope that the transaction and confirm that all processing executed successfully and ready to commit. Commit phase then calls each resource to the commit its processing. Rollback. If an error occurs in either the begin or commit step, roll back to the options within the transaction so that no one part results in the partial completion. Here you can see a request client is connected to the HTTP via request HTTP, and add message queue are in reliable acquisition flow. HTTP is connected to the add message queue, and here the HTTP is connected to the client via status response, and here the add message queue is add message to the queue is connected to the VM. VM interacts with the reliable acquisition flow and application logic flow. VM is connected to the consume message from the queue. Consume message from the queue, flow ref to the business logic subflow, and add message to the queue are in application logic flow transaction 1 here. Consume message from queue is connected to flow ref to business logic subflow, and it is connected to add message to queue, and it is connected to the VM. Here you can see Anypoint Cloud Hub default deployment model. If the application uses multiple workers, Cloud Hub deploy the worker in a separate availability zones by default. Provide HA across availability zones. The distance between availability zones is variable and generally doesn't exceed 350 miles. If an application uses a single worker, then the availability zone is unavailable. Cloud Hub automatically restart the application in a different availability zone. In this case, the application might experience downtime. You can set up status.mulesoft.com to receive alerts when the failure occurs in an availability zone or region. Here you can see Mule interacts with region, and Mules interacts with region and availability zone. Availability zone interacts with the other availability zones. Here availability zones are in the region, and here the again availability zones are in the region. Here the Mule region and availability zones are Mule and regions are in Amazon Web Services. Here you can see suggested alternative deployment model. You can use the load balancer or load balancer cloud or on premises for applications deployed to a different regions to provide better disaster recovery strategy. Here you can see region and regions and Mule in Amazon Web Services. Here availability zone sign the regions. Mule interacts with the region and the availability zone. Here mules are connected to mules interacts with the load balancer. Here you can see a virtual private cloud in Cloud Hub. Anypoint virtual private cloud VPC offering allows you to create virtual private and isolated network segment in the cloud to host your Cloud Hub workers. Connecting to your Anypoint VPC extend your corporate network and allow Cloud Hub workers to access resources behind your corporate firewall. You can connect to the on-premises data centers through a secure VPN tunnel or transit gateway attachment, or connect private AWS VPC to your Anypoint VPC through VPC peering or AWS Direct Connect. The base Anypoint VPC subscription includes 2 Anypoint VPCs, and each Anypoint VPC can associate with the multiple environment. This allows you, for example, to have one isolated network for your production environment and another for your non-production environment. For example, QA and staging. Your license requirements depend on your specific deployment scenario. Anypoint VPC support different Amazon regions. During setup, you need to specify which Amazon region you want. You can even have multiple Anypoint VPCs inside the single Amazon region. Each Anypoint VPC allow you to configure firewalls rules to apply to your workers. You can choose to expose or block your custom ports, or even blocks request to apps coming from the Cloud Hub shared load balancer. If you use dedicated load balancers, you can configure one or more dedicated load balancer to validate requests using your own SSL certificate and to map input URLs calls to the different Cloud Hub applications. Combining firewall rules and dedicated load balancers configuration enables you to fine-tune how external services reach your applications. Here workers are inside production VPC here, and here the workers are inside non-production VPC. Here you can see the IP addresses. Here the production VPC and non-production VPC are in region US East 1, and region is inside Cloud Hub. Here the production VPC interacts with your network, and also non-production VPC interacts with your network, and devices, users, and office buildings are in your network. Here you can see the default Anypoint VPC architecture in Cloud Hub. The Anypoint VPC is logically private and isolated network hosted inside Cloud Hub. You can connect to a private intranet to your Anypoint VPC as if they were all part of a single private network. Anypoint VPC configuration exposes the DNS record mule-worker-internal, then app name .cloudhub.io. This DNS record, which includes the IP address of all your workers, this DNS record cannot be accessed from outside your Anypoint VPC. Each Anypoint VPC allows you to configure firewall rules to check inbound connections directly to your workers. For firewall rules created by default, two rules by default two rules that allows you private address space to connect through the ports HTTP ports 89, 8091 and 892, and rules that allow external request proxies by the Cloud Hub shared load balancer. And here the 881 and 882 also here, and the shared load balancer ports through 881 and 882 here. All traffic that is not allowed in the firewall rule is blocked by default. Here graphic shows the default Anypoint VPC architecture. Here you can see public internet is connected to DNS record here. Here the shared load balancer, DNS record, and here the VPCI in Cloud Hub. Here the DNS record is in the shared load balancer. Here the DNS record, here the HTTP ://appname.region.cloudhub.io, and it is connected to DNS record via HTTP 881 88 HTTP and 882 443 HTTPS to the DNS record. Here the you can see the DNS record. Here the HTTP :// mule worker app name .region cloudhub.io port, and DNS record is connected to firewall rules here. Here worker app names, firewall rules, and DNS records are in VPC here. Here the VPC 10.10.0.0/24. Here the here there's a DNS record. The DNS record interacts with IPsec tunnel, VPC peering, and direct connect. Here you can see the DNS records. HTTP :// mule worker internal app name .region.cloudhub.io 8091, and same with 8092, and DNS record is connected to firewall rules. Here the firewall rules are connected to worker app name. You can configure here you can see the Anypoint VPC architecture with the dedicated load balancer. You can configure a dedicated load balancer inside your VPC, which allows you to provide custom certificates and and optionally enforce a two-way SSL. Allows you to two-way SSL client authentication. If you configure proxy rules that map your applications to the custom domains, you can, for example, host everything under single vanity domain. This graphic shows the Anypoint VPC architecture with the dedicated load balancer. Cloud Hub dedicated load balancer is assigned to a particular Anypoint VPC. Dedicated load balancer then routes the traffic to that particular Anypoint VPC. within the particular service region of the VPC. Each dedicated load balancer has a DNS record. ib-name dot lb dot anypoints dns dot net or lb name lb prod eu rt dot any point dns dot net for EU control plane. That resolves the two public IP addresses of its two instances. Through your DNS provider, you can add a CNAME record pointing to the dedicated A record and use your own domain names to access it. The DNS A record can also be reached from outside the VPC. Additionally, a CloudHub dedicated load balancer has an internal domain name to be used by the applications and clients within the Anypoint VPC. The structure is internal dash lb dash name dot lb dot anypoints dns dot net. Here you can see public internet is connected to SSL endpoint. Here the http :/api.yourdomain.com/app-name. Here the dedicated load balancer and mapping rules and DNS record and firewall rules and worker app names are in VPC. Here the DNS record and SSL endpoints interacts with the two-way TLS, and here you can here the internal dash lb dash name dot lb anypoint dot net /app name. This DNS record, DNS record interacts with the IP sec tunnel, VPC peering, and direct interact via direct connect for the internal network. And here the dedicated load balance is connected to mapping rules. Here the lb name dot lb anypoint dot net /app name and app name dot cloudhub.io. Here mapping rules are connected to DNS record via 8091 80 HTTP and 8092 443 HTTPS. Here the DNS record. Here the http :/mule worker internal app name dot region cloudhub.io 8091 and 92. The DNS record is connected to firewall, and firewall is connected to app worker app name. Here the VPC and DNS record and shared load balance are in CloudHub. Here the 8081 80 HTTP 882 443 HTTPS are connected to DNS record. Here http :/mule worker app name dot region dot cloudhub.io dot port. Here the DNS record is in shared load balancer, and here the http :/app name dot region dot cloudhub.io. Here you can see IPsec tunnel in CloudHub. You can use the IPsec tunnel with the network to network configuration to connect your on-premises data centers to your Anypoint VPC. An IPsec VPC tunnel is generally the recommended solution for VPC to on-premises connectivity, as it provides the standardized, secure way to connect. This method also integrates the well-existing IT infrastructure such as routers and appliances. Note, if you are using legacy VPN, and migrate to Anypoint VPN before making changes. To create Anypoint VPN connection to your network, see the Anypoint VPN in the documentation. Here you can see Anypoint with the worker sign Anypoint VPC, and Anypoint VPC is in the Cloud Hub, and it's interact with the Cloud Hub external gateway IP address here. And Cloud Hub external gateway IP address is in IP address interacts with the UI external gateway IP address via IPsec tunnel, and it's interacts with the firewall, and firewall interacts with the on-premises data center here. Data center inside on-premises data center here. Sorry, data center inside on-premises data center here. Here you can see transit gateway attachments. AWS transit gateway act as a cloud cloud router in AWS, simplifying the network access between EPC on premises data centers and third-party software, while providing increased visibility and control over the network. Transit gateways effectively match your organizational cloud resources and on-premises data centers into one network topology. On Cloud Hub, you can take advantages of this network's implication by securely attaching Anypoint VPC to an AWS transit gateway in your AWS account. To use the transit gateway attachment, use your Anypoint VPC and AWS transit gateway must be in the same region. Here workers are in Anypoint VPC, and Anypoint VPC is in Cloud Hub, and Cloud Hub and AWS VPC and transit gateways are in AWS region, and Anypoint VPC interacts with the transit gateway via VPC attachment, and transit gateway interacts with the Anypoint VPC via VPC attachment, and AWS VPC via VPC attachment, and on-premises data center via VPN. Here the transit gateway, AWS VPC, and on-premises data center are in your network, and data centers are in your AWS VPC and in the VPC, and data centers are in on-premises data center. This is the firewall. Here you can see VPC peering. VPC peering provides the connection between your two VPCs. In this case, it pairs your private Amazon VPC directly to your Anypoint VPC. This enables you to route traffic between two VPCs so that so they can communicate as though they are in the same network. Here you can see workers are in Anypoint VPC, and Anypoint VPC is in Cloud Hub, and Cloud Hub and AWS VPC are in the AWS region. Anypoint VPC interacts with the AWS VPC via VPC peering connection. Data centers are in the AWS VPC. Now we are considering AWS Direct Connect in Cloud Hub. To create a direct connection to Anypoint VPC, create or leverage the existing AWS Transit Gateway on your AWS account and set up the direct connection to the Transit Gateway. Then attach Anypoint VPC to the transit gateway and configure the required routing to enable the Anypoint VPC on-premises connectivity. Note, to use the direct connect, your AWS direct connect partner and the Anypoint VPCs must be located in the same region. Direct connect gateways are not supported. Direct connect requires the use of broader gateway protocol BGP for dynamic routing. For higher availability, use multiple direct connect connections from the different AWS direct connect locations. Here you can see workers are in Anypoint VPC and it is in Cloud Hub, and Cloud Hub and your network are in the AWS region. Anypoint VPC interacts with the transit gateway via VPC attachment. Transit gateway interacts with the on-premises data center via AWS Direct Connect, and data centers are in on-premises data center, and a transit gateway and on-premises data center are in your network. Here you can see how a load balancer interacts with VPC and Anypoint platform. Routing internal requests to the dedicated load balancer. The Cloud Hub dedicated load balancer has an internal domain name. The internal domain name that is used by the application and clients within the Anypoint VPC. Internal domain uses the following naming convention. LB-name is the name you give to the load balancer when you create it. It's internal-lb name .lb.anypointdns.net. Each DLB and has DNS records. lbname.lb.anypoint.dns.net that resolve to the public IP addresses correlated to the number of workers. Through your DNS provider, you can add CNAME record pointing to the record and use the domain names to access it. If you want your load balancer to merge all connections to your applications but do not want to default domain name for your application publicly exposed, then the application must listen to the HTTP port 80 or port 8091 or 8092. Alternatively, you can create a custom mapping policy to direct outside request from your load balancer to a specific applications. The following diagram shows how a load balancer interacts between VPC and Anypoint platform. Load balancer listens from outside request or HTTPS, and by default they communicate internally with the worker over HTTP. If you configured your Mule application within the Anypoint VPC, to listen to HTTPS, you must set the upstream protocol to HTTPS, then creating the mapping list by using the load balancer mappings add command. Internal HTTP mod lets you to configure how HTTP requests are managed. They are either silently ignored. It's mapped HTTPS on default SSL endpoint, or URL is mapped straight to the corresponding HTTPS URL. Here the LB management service perform LB management, LB deployment and recovery procedures based on the customer request and checks performed in recurring basis. Instance presence check runs every minute. Instance impaired check status check which checks the degraded hardware or services, run every 5 minutes. Check the will trigger recovery if needed. Here the services and LB management service are inside the Anypoint platform. LB management service is connected to load balancer here. Here the watchdog and LB process are in load balancer here, and watchdog checks once a minute if LB process has failed, so that the LB management service can recover when there is a failure. Here it is HTTP 80 and HTTP S443 HTTPS 443 via public DNS is connected to LB here. Here the LB is connected to apps. Here the via HTTP 8091 or HTTPS 8092 via internal DNS. Apps inside customer VPC or VPC. Here the public access via 8091 and 8092 are connected to app 1, app 2, app 3 is not possible here. Here you can see Cloud Hub 2.0. At MuleSoft Connect 2022, we announced their Cloud Hub 2.0. This new release builds the on success of existing Cloud Hub infrastructure by bringing the brand new deployment experience and containerized architecture based on the Kubernetes. With this update, users can quickly deploy their integrations, APIs, and automations to a resilient, scalable environment. Today, we are thrilled to announce this to environments. Here, you can see the Anypoint control pane. It's interact with the Anypoint monitoring analogs, object store version 2, and runtime manager, Anypoint exchange, and access management. This interacts with the MuleSoft platform services. MuleSoft platform services interacts with the worker nodes, and here the Cloud Hub 2.0 shared space VPCs are here. Here you can see the worker nodes, and here the orchestration services. Here you can see Cloud Hub architecture. MuleSoft defined a Cloud Hub as a cloud-based integration platform as a service, IPaaS, that enable developers to integrate and orchestrate applications and services while giving operations and control and visibility they required for mission critical demands, without the need to install or manage middleware or hardware infrastructure. You can deploy applications to Cloud Hub through Anypoint Anypoint runtime manager found on the Anypoint platform. Comparing Cloud Hub with other app deployment scenarios, Runtime Fabric, customer hosted, private cloud foundry. It is the easiest option for deploying Mule applications. However, the applications Cloud Hub as itself and Mule applications are deployed, executed under AWS infrastructure. For example, and specifically each deployed application is running under EC2 instance with the Linux or Mule runtime with JVM. How each instance per work is more complex than it may seem. Cloud Hub workers also execute CloudBus system services on the OS. And Mule runtime, which are required for the platform capabilities provided by Cloud Hub, such as monitoring of Mule application in terms of CPU, memory usage, number of messages, errors, etc., which allow Anypoint platform to provide analytics and alerts based on the matrices. Auto restarting failed Cloud Hub workers, including failed Mule runtime and on the otherwise functional EC2 instances. Load balancing only to healthy Cloud Hub workers. Provisioning of new Cloud Hub workers to increase or reduce capacity. Persistence using object stores of message payloads or other data across the Cloud Hub workers of a Mule application. DNS entries for Cloud Hub workers on and Cloud Hub load balancer. Each Mule application is assigned a DNS name maintained by the AWS root. Here Amazon AWS platform services are connected to naming, persistence, load balancing, and AWS platform services interacts with the provisioning and auto start. Here the persistent is connected persistence, provisioning, load balancing, and auto start are connected to HA and scalable execution. It interacts with the Cloud Hub worker. Here the auto restart is connected to Cloud Hub auto restart and load balancings are connected to Cloud Hub system services in Cloud Hub worker. Here the monitoring and alerting of API implementations is connected to Cloud Hub system services in Cloud Hub worker. Cloud Hub system services, Mule runtime, Linux, and policy holder search implementation are in Cloud Hub worker. Here the Cloud Hub system services are connected to Linux, and here the Cloud Hub system services are connected to interact with Mule runtime, and Mule runtime interact with the Linux. Here the backend system interact with the Mule runtime and policy holder search implementation. Here the fault tolerant API invocation interact with the Mule runtime and policy holder search implementation. Policy holder search RAML definition is in policy holder search implementation. Here you can see the high level architecture in which the API implementations running on each Cloud Hub worker involved worker invoked. Each Mule application is assigned a DNS name maintained by the AWS root 53 service. In turn, it also received the two other known DNS names that resolved all the Cloud Hub workers of the Mule application. The following diagram represents the high-level architecture in which the API implementations running on each Cloud Hub worker are invoked. The client certificates associated with the Cloud Hub load balancer only work if it is a dedicated LDB, not a shared load balancer SLB. In case of using shared load balancer, the default certificate of Cloud Hub will be applied, and the certificate applied in the HTTP listener component will be replaced by the one in the Cloud Hub. Here you can see API client is connected to a Cloud Hub load balancer via HTTP or HTTPS, and the API client is connected to Cloud Hub worker 1 and the worker N via HTTP or HTTPS here, and the API client is connected to Amazon root 53 via DNS lookup, and Amazon root 53 is connected to Cloud Hub load balancer. Cloud Hub load balancer interacts with the client certificate, and it is optional, and Cloud Hub load balancer is connected to Cloud Hub worker 1 and worker N via HTTP or HTTPS. Here the API implementations are in Cloud Hub workers here. Here you can see the Mule events in Mule runtime. A Mule event contains the core information processed by the runtime. It travels through the component inside your Mule app following the configured application logic. Note that the Mule event is immutable, so every change to an instance of a Mule event results in the creation of a new instance. A Mule event is composed of these objects. A Mule message contains message payload and its associated attributes. Variables are Mule event metadata that you use in your flow. Here you can see attributes and payloads are in Mule message, and Mule message and variables are in Mule event. Here you can see a Mule message structure in Mule runtime. Mule message is a part of the Mule event that serves as a container for message content and metadata, typically from external sources, as it is processed within the flows of a Mule app. Mule message is immutable, so every change to the Mule message results in creation of a new instance. Each processor in a flow receives a message, returns a new Mule message consisting of these parts: message payload, which contains the body of the message, for example, the content of a file, a HTTP body, a record from a database, or a response to a REST or web service request. Message attributes, which are metadata associated with the payload, such as HTTP headers and query parameters. Here the attributes. Mule event source triggers a process that creates a Mule event with the Mule message and execute the Mule flow that contains the event source. For example, this process begins each time the HTTP listener source receives the request to the scheduler executes. After a flow begins its execution, downstream process such as co-component, file read operation, so HTTP request operation can then retrieve, set, and process Mule message data, payload, and attributes that reside in the Mule event according to their configurations. Note that in Anypoint Studio, the Data Science Explorer shows the structure of a message at any given point of the flow. Message payload. The message payload contains the content of the body of the message. For example, a payload contains the result of HTTP request, the content of records you retrieve through the selection operation of the database connector, or the content of a file you retrieve through a read operation to a file or FTP connector. Attributes contains the metadata associated with the body or payload of the message. The specific attributes of a message depend on the connector, such as HTTP, FTP file associated with the message. Metadata can consist of headers and properties received or returned by the connector, as well as other metadata that is populated by a connector or through a core component, such as a transform message. Here you can see attributes and payload are in Mule message. Here you can see Mule errors. Here the Mule error types. In Mule runtime, Mule errors have a namespace such as HTTP and file, an identifier such as not found. They belongs to a hierarchy of error types. Naming conventions enable you to distinguish the errors according to their domain. For example, instead of throwing not found, the HTTP connector can throw HTTP colon not underscore found. The file connector can throw file colon not found errors. Unlike connectors, Mule runtime errors have an implicit Mule namespace, so Mule colon expression and expression are interpreted in the same way. Error types can have a parent type. For example, parents of HTTP colon unauthorized is Mule colon client underscore security. And the parent of Mule colon client underscore security is Mule colon security. This hierarchy implies each error type is a specification of more global error type. For example, an HTTP colon unauthorized error type is the type of a client security error. Mule colon client security, which is a type of a more broad security issue, Mule colon security. Hierarchies enable you to route errors in a general or more specific way. For example, an error handler or Mule colon security catches an HTTP colon unauthorized errors and auth errors. The follow figure shows the core runtime hierarchy. All errors belongs to one of these two main types, any and critical. Each type under any is matched by its parent and can be handled, while error types under critical are so severe that cannot be handled and are only logged. Critical errors include fatal JVM error and overload. Whenever there is no clear reason for a failure, a component can use the unknown type. You handle this error through any type to define unclear errors without changing the existing behavior of the app. For connectors, for each connector, define its error type hierarchy considering core runtime hierarchy through connectivity. And retry exhausted. types are always present because they are common to all connectors. Error types, any error type that matches all error types that occur in the flow can be handled. This type does not include errors that occur on the source. Transformation indicates an error occurred while transforming a value. This involves the Mule runtime internal transformations and not data wave transformations expressions. Indicates an error occurred while evaluating the data view expression. Validation indicates an validation error occurred. Duplicate message indicates a validation error regarding a message being processed twice. For example, using independent message validator. Redelivery exhausted indicates that the max attempts to reprocess a message from a source have been exhausted. Connectivity indicates that there was a problem establishing connectivity connection. This could occur while using a connector, for example, HTTP requester. Retry exhausted indicate that the retries of a certain execution block have been exhausted. For example, for a given operation or using until successful scope. Routing indicates an error occurred while routing a message, for example, using a round robin router. Composite routing indicates that one or more errors occurred while routing a message, for example, scatter gather router. Security indicates the security error occurred, the like invalid credentials being received or expired token being used. Client security indicates an external entity calling an external endpoint produces a security error. Server security indicates a security error enforced by the runtime Mule runtime. Not permitted indicates a security restriction enforced by a filter, for example, using the authorization filter of the Mule Spring module. Stream maximum size exceeded indicates the maximum size allowed for a stream has been exceeded. For timeout indicate timeout occurred while processing a message. Unknown indicates an unknown or unexpected error occurred. This cannot be handled directly, only by handling any to ensure backward compatibility in case more error types added in future runtime versions. Source indicates that error occurred in the source of the flow. These errors cannot be handled. A source error response generate indicates that an error occurred in the source of the flow, generating the parameters of an error type, error response. This error cannot be handled since the source has already executed the failing path. Source error response send indicates that an error occurred in the source of the flow sending an error response. This error can be handled since the source has already executed the failing path. Source response indicate that the error occurred in the source of the flow while processing a successful message. These errors can only be propagated since the source already executed the successful path. These errors cannot be handled. Source response generate indicate an error occurred in the source of the flow while generating the parameters of the successful response. Source response send indicate an error occurred in the source of the flow while sending a successful response. Critical indicates the severe error occurred. These errors cannot be handled. Overload indicates the problem of overloading occurred and execution was rejected. Flowback pressure indicates the problem of overloading occurred at the source level, for example, using HTTP listener as a source. Fatal JVM error indicates a fatal error occurred, such as stack overflow. Here you can see errors, and errors are connected to any or critical, and in critical you can see the types unknown, transformation, routing, connectivity, and it has subtype. Connectivity is connected to retry exhausted, and connectivity and expression and security. Security has client security and server security. In the critical errors, you can see a fatal and overload. Here you can see how resources exported by Mule dash artifact.json are applied within the app in Mule runtime. In the class loading isolation mechanism, once APIs are clearly defined, you can prevent access to internal classes of artifact and only make the public API accessible from outside. To protect the API, Mule for users the custom class loading mechanism. Consider the and the following mule-artifact.json descriptor file for the extension here. The following diagram shows how resources exported by Mule artifact.json are applied within the app. Artifact class loader, a regular Java class loader pointing to a Java files included in the extension. This class loader loads all files and classes of the extension. Artifact filtering class loader, a wrapper created over the artifact class loader, which enforces access restriction to the extension code for the foreign artifacts app or other plugins. It uses the content of the mule-artifact.json descriptor to determine what is public. Extension code. The Mule extension code uses artifact class loader, which does not have any restriction, and it is only able to locate resources of the plugin itself. Application code, the Mule app code, it uses the artifact filtering class loader of the extension to prevent the app from accessing restricted code or resources. Here you can see application code is connected to artifact filtering class loader via load resources, and artifact filtering class loader is connected to application descriptor via filter with, and the artifact class loader is connected to artifact filtering class loader is connected to artifact class loader via delegates to, and extension code is connected to artifact class loader via load resources. Here you can see a simple flow in Design Center in Mule flows in Mule runtime. Understanding the basic flow architecture is the key to understanding a Mule application. Essentially, every Mule flow contains a series of Mule components that receive or process messages. At the simplest level, flows are a sequence of processes. A message that enters a flow can pass through a variety of processes. In a typical flow, a Mule application receives a message through a source such as an HTTP listener component. Transform that message into a new format. And process any business logic before writing the process message to an external system in a format that the system can read. To separate processing into more manageable units, Mule applications often contain multiple interrelated flows instead of just single flow. One flow can call another flow as a direct reference. Here you can see HTTP listener / source is the payload any attributes HTTP request attribute, and HTTP listener is connected to transformed data view. Here payload object and attributes HTTP request attributes, and transform data view is connected to database connectivity, and insert payload statement result attributes HTTP request attributes, and database connectivity insert is connected to logger info, payload is statement result. Here you can see async scope in Mule runtime. The async scope is a branch processing block that executes simultaneously in the main flow. The main flow continues to execute while it initiates and processes the async scope. The flow does not have to pause until the last message processor embedded in the asynchronous flow has completed the task. Async can be useful for executing time-consuming operations that do not require you to send a response back to the initiating flow, such as printing a file or connecting to a mail server. To facilitate simultaneous branch processing, async scope send one copy of the message it has received to the first embedded message processor in its own processing block. At the same time, it sends another copy of the message to the next message processor in the main flow. Because the async scope is executed in fire and forget manner, the result of the processing within the scope is not available in the main flow. Here you can see the message process is connected to scope here. The async here you can see async scope and embedded asynchronous processing block. Here the scope is connected to the processing block and next processing block, and here the scope is connected to the main flow here, the next processing block. Here you can see a batch processing architecture. The Mule batch processing components prepare records for processing in the batches, run processes on those records, and issue a report on the result of the processing. Record preparation and reporting take place within the batch job component. Processing takes place within one or more batch step step components, and optionally a batch aggregator component within a batch step component. Processes you place within a batch processing components act on records. Each record is similar to a Mule event. Processes can access, modify, and route each record payload using a payload keyword, and they can work on Mule variables using vars. However, they cannot access or modify the Mule attributes from the input to the batch job component. Here you can see the Mule flow. Message source is connected to message processors, one or more. Message process are connected to batch job scope. Here the process record, and this is on complete. Here the batch job process records and on complete are in batch job scope. Here the batch steps scopes are in process records. Here the record processors, one or more, is connected to batch aggregator, optional, and record processors and batch aggregator are in the here the batch step scope, and record process are in batch aggregator here, and batch scope step scope is connected to another batch step scope. Record process, one or more, are in the batch step scope, optional here. report processor recommended is on complete. Here you can see batch job phases. Each time a batch of phases in Mule runtime, each time a batch job component execute, the following phases take place. One, load and dispatch phase. Batch job component splits valid input into records and prepare the records for processing. This phase takes place within a batch job component. Process phase. Mule components and connector operates within one or more batch step components in a batch of processes. Process records within a given batch job instance. Process within a batch aggregator component also occurred in the process phase. On complete phase, the batch job component issue a report object with the result of processing a batch job instance. Here you can see the phases: load and dispatch phase, process phase, and on complete phase. Here you can see the process phase in batch job phases in Mule runtime. The process phase begins after a load and dispatch phase finishes. Loading records to the queue and start execution of a batch job instance. In this phase, batch job components concurrently pull records of the configured size of the queue to process them. The default batch block size is 100. Within batch step component, processing takes place in parallel at the block level, but records within each block process sequentially by default. Mule uses auto-tuning capabilities to determine how many threads to use and level of parallelism to apply. During this phase, processes within the components can access and modify the record using payload and vast Mule variables. The batch job component consumes records after all record processing finishes. So any transmission of the process records to an external server or service must take place within the batch job step or batch aggregator components. After processing records in a block, the batch step send the records back to the stepping queue, where the records wait for the next batch step component. This process continues until every record phase go through the every batch step component within the same batch job component. At the end of this phase, all records are consumed. They are not available for further processing by downstream processors in the Mule flow. Note that since the changes to records that take place within the batch aggregator component are not propagated outside of the batch aggregator component, changes are not visible to subsequent batch step component in the flow. As processing takes place, each record keeps a track of all the batch step components that process it. Here you can see the record stepping queue. Record stepping queue is connected to batch steps here. Here the batch is connected to batch step 1, and here the record processor in batch step 1 here. Record processor is connected to next record processor and is connected to next record processor, and it is the last one is connected back to the record stopping queue. And here the record stopping queue is connected to batch step 2. Likewise, then batch step 3 here, and also batch step 3 likewise here. Here you can see the behavior when a batch aggregator component sets a fixed size. By default, the batch job instance does not wait for all the queued records to finish the processing in one batch step component before making them available for processing the next batch step component. Configuring a batch aggregator component changes this behavior. Here's behavior when the batch aggregator component set a fixed size. The processor within the batch aggregator must be able to receive any array of records as inputs. One here, the each batch step component within the batch job component received one or more records blocks and start processing them in parallel. Two, here the after processing a record, batch step component send the records to the batch aggregator component for further processing. Three, here the when set to process the fixed size, the aggregator component arrange the record into one or more blocks containing a specified number of records. If fewer records are available than the configured size, then the last block of record is smaller. For after processing records in a given array, the batch aggregator component send all the records back to the stepping queue. Here the record stepping queue is connected to batch step, and batch step is connected to aggregator fixed size, and it's connected to did the array of records reach its configured size. If it is no, it's connected back to aggregator fixed size, and if it is yes, it's connected to record stepping queue. Here you can see the behavior when batch aggregator component is configured to stream records in Mule runtime. Behavior when batch aggregator component is configured to stream records. When streaming, the batch aggregator component processes record as soon as it receives them, instead of putting them into record blocks. No record is exposed to the next batch step component in the flow until all records in the aggregator processes all records in the current batch step. The processor within the component must be able to accept an array of records as input. One here, the each batch step component receive one or more record blocks and start processing them in parallel. After batch step processes a record, the batch step send the record to the batch aggregator for further processing. The batch aggregator component continues processing record until there are no more records in the stepping queue that are awaiting to be processed by the current batch step. For the batch aggregator component send all aggregated records to the stepping queue. The Mule retains a list of all records succeeded or fails processed through each batch step, and in the event of processor in a batch step fails to process a record, Mule continues processing the batch, skipping over the failed record in each subsequent batch step process step based on the accept policy. The batch step component provide the max fail record property for setting the number of record that can fail before the batch step stops. Here you can see record stepping queue is connected to batch step. Batch steps is connected to aggregate streaming, and it is connected to any records in the queue for this step. If it is no, it's connected to back to aggregator streaming. If it is yes, is connected to these records are connected to record stepping queue. Here you can see a schematic diagram of a choice router with three options, one being the default option. In Mule runtime, the choice router dynamically routes messages through a flow according to a set of data view expressions that evaluates message content. Each expression is associated with a different routing option. The effect each expression is associated with a different routing option here. The effect is to add conditional processing to a flow similar to a if then else code block in most programming languages. Only one of the routes in the choice router executes meaning at the first expression that evaluates to true triggers the root execution and the others are not checked. If none of expressions are true, then the default root executes. Here you can see a choice, and choice is connected to routing options here, and here the default routing option. Here you can see the order of processing when one flow references another in Mule runtime. The flow reference routes the Mule event to another flow or subflow, executes all processes in the reference flow, and then routes the event back within the same Mule application. The following diagram shows the order of processing when one flow references another. When the main flow is triggered, the Mule event travels through and then execute the flow until until the event reaches the flow reference. Event then travels through and execute the reference flow from beginning to end, and then returns to the main flow. This process enables you to treat the entire reference flow like a single component in your current flow. This flow reference breaks the Mule application into discrete and reusable units. For example, a flow that lists files on a regular basis might reference another flow that processes the output of the list operation. Instead of appending all the processing steps to the flow that lists the files, you can append the flow reference that points to the processing flow. Here you can see the main flow and here the reference flow. Here 1, 2, then flow reference, and then 3, 4, 5, then 6, then 6, 7. Here you can see on error propagate in on error components in Mule runtime. Executes but propagate an error to a higher level, such as containing scope. For example, a flow that contains try-scope where the error occurs, or external flow containing the flow reference to the flow in which the error occurs. The error breaks the owner's execution and propagate to that high level, causing a failure at the level. In addition to any transaction, the owner handle is rollback. However, note that the transaction is not rollback if another component, one that does not own on error propagate, created the transaction. Here the try scope and on error propagate is in the flow. Here the flow error handler. Here the 1 is connected to 2, 2 and 2, 3 and others are in the try scope here. 2 is connected to 3, and 3 in 3 error is moved to 4 in the error propagate, and 4 is connected to 5 on error propagate, and then the 6 then this is 6 in error flow handler, and 6 is connected to 7 in error flow handler. Now we are considering architecture in scheduler endpoint trigger in Mule runtime. Like other Mule event source component, the scheduler is the first component in the Mule flow. The XML for the scheduler consists of the following element: scheduler, the top level element of the scheduler, scheduling dash strategy, second level element that accepts one of the following children: fixed frequency for common scheduling frequency such as every second, cron, the cron expressions and time zone settings. Scheduler sets a scheduling strategy at a fixed frequency or interval based on the cron expression. For example, fixed frequency setting in the schedule execute every 15 seconds. Cron expression, or the cron expression in a scheduler triggers the generation of mule message in a new execution of the flow every 15 milliseconds. At least one processor must follow the scheduler. Processors include mule components and connect operations such as HTTP request operation or transform message component. Failure to provide the processor produces a mule runtime exception and causes the deployment of the mule application to fail with the following error message in logs. Error mule runtime exception, the content of the element flow is not complete, etc. Here the scheduler and processors are in the flow example here, and this is error handling. Schedule is connected to a processor and processor connected to the another processor here. Here you can see the behavior of scatter gather component in mule runtime. Scatter gather component is a routing event processor that processes a mule event through different parallel processing routes that contains different event processors. Each route receives a reference to the mule event and execute the sequence in one or more event processors. Each of these routes uses separate thread to execute event processors, and the resulting mule event can be either the same event processors, and it can be either same event without modification, or a new same event, or the new mule event with its own payload, attributes, and variables. The scatter gather component then combines the mule events returned by each processing route into a new mule event that is passed to the next event processor. Only after every route completes successfully. The scatter gather component execute each route in parallel, not sequentially. Parallel execution of routes can greatly increase the efficiency of your mule application and may provide more information than sequential processing. The scatter gather component works with repeatable streams. It does not process non-repeatable streams, which can be read only once before they are lost. By default, all streams are repeatable in mule unless the component stream strategy is configured to be non-repeatable. The following diagrams details the behavior of the scatter gather component. The scatter gather component receive a mule event and send a reference of this mule event to each processing route. Each of the processing route start executing in parallel. After all processors inside the route finish processing, the route returns a mule event, which can be either the same mule event without modification, or the new mule event created by processors in the route as a result of the modification applied. 3. After all processing routes have finished the execution, scatter gather component create a new mule event that combines all resulting mule events from each route and then passes the new mule event to next component in the flow. Warning: configure your scatter gather component to have at least 2 routes, otherwise your mule application throws an exception and does not start. Here mule event is connected to scatter gather component, and here the it's break into event processors. Here you have 3 event processors, and event process connected to mule event again. Connected to mule event here. Here you can see the REST Studio project in API Kit Anatomy in Mule runtime. The REST-SOAP Studio project that uses API Kit has the following parts. REST-SOAP interface, the main flow and backend flows, The REST interface, the relationship between REST resources and actions is called resource action pairing. The interface exposes internal data assets requested by the REST service. Also, the interface defines the API designing resources that contain no access and specify actions such as get and put on the example data. Here you can see API console interact with RML. Here you can see the flows, API main, and the listener and the router error handling. Here the flow 1 and here the flow 2. Here you can see the SOAP Studio project in API Kit Anatomy in Mule runtime. The SOAP interface, the interface defined by WSDL file exposes the number of services. Each service has a set of operations. Underlying types of data is XML defined by schemas within WSDL file or by an imported XSD file. Here the main flow for the API manages these functions, exposes API using Anypoint connector for HTTP connector, routes requests between interface and backend flows based on the HTTP request, accept requests and send and facilitate communication between interfaces and API processes. The main flow consists of HTTP listener, API Kit REST or SOAP router components. API Kit router is the key message processor that validates the request against the provided definition, enriches messages, for example, by adding default values to the messages, and routes requests to the particular flow. And also routerizes error messages if errors occurs while routing, validating, or processing the user request. Backend flows. API Kit for REST generate a backend flow for each resource action pairing in the RML file. In the API Kit for SOAP generates backend flow for each operation in WSDL. Here you can see SOAP UI interacts with WSDL, and here the main flow. Here the main flow, and here the listener and the router. Here the flow 1, flow 2. Here you can see RML scaffolding in Mule runtime. Start a new API project using an API definition file. Use this method if you want to start a project by either importing an existing RML or WSDL file, or by referencing the file URL. Select file, then new, then Mule project. There are two in the project name. Enter the name of the project for the export. For the example, my project, and select or accept the default EE runtime. For example, Mule Server 4.0.0 to 4.2.0 EE. In the implementation, select specify API definition file location or URL. In location, do one of the following. If you created an api.rml file in Design Center, select Design Center, log into Anypoint platform if necessary, and select api.rml. If you didn't create a RML file in Design Center, select Browse Files and select the RML or WSDL file that you created. If you didn't create RML file in Design Center, select Browse Files and select RML or WSDL file that you created in the text editor. For a WSDL file, select a service and port from the drop-down menus and accept the default. Then accept the location default options and click File. Click Finish. Using this method, API Kit scaffolding technique generates an archetype that contains basic configuration files, put plus a Mule XML for configuration file, an implementation of API. For RML based APIs, RML file appears under source main resources API folder. The implementation of the API contains the main flow with the HTTP listener, API Kit router component, error handlers, RML dependencies, push or pull changes from one location such as studio to the other such as design center. Backend flows containing REST resource action mappings. For WSDL based APIs, the WSDL file API under the source main resources API folder. Implementation of the API contains a SOAP router, SOAP and other components. Here the RML based API, the RML file appears under source main resources API folder. The implementation of API contains the main flow with the HTTP listener, API kit router component, error handlers, RML dependencies, push and pull changes from one location such as studio to other such as design center. Backend flows containing REST resource action mappings. Here you can see RML is connected to scaffold. Scaffold is connected to here the API main. Here listener is connected to API kit router, and API kit router is connected to here, and you can see the here error handling. Here the main API, and here the listener and router and error handler. Here you can see WSDL scaffolding in Mule runtime. For WSDL based APIs, WSDL file appears under source main resources API folder. In the implementation of the API contains SOAP router, SOAP fault response template, backend flows containing SOAP messages templates. Here the WSDL is connected to scaffold. Scaffold is connected to the API main. Here the listener is connected to the SOAP router, and SOAP router is connected to here, and the you can see the error handler here. This is XML config, and here you can see the API main, and here the listener, and here the router. Here the API main is connected to XML config. Here you can see the setting a target variable. Target variable changes the typical course of message through a flow in enriched data with target variables in Mule runtime. Here the normally an operation outputs a different message than it received as input. Here the original payload is connected to component A. Component is A interacts with payload modified by A. Component A is connected to B via payload modified by A, and component B is producing output via payload modified by B. Here you can see the setting a target variable changes the typical course of message through the flow in enriched data with target variables in Mule runtime. Here the in this case the component C receives the same message that B received from A. However, when you set a variable from an operation, the operation outputs to the next component in the flow the same message that is received as input. For example, assume you have a flow consisting of component A followed by component B with the target value of my message. Then the component C and then component C. In this case, the component C receives the same message that B received from A. Here the original payload is connected to component A. Component A is connected to component B via payload modified by A. Component B is connected to set target my message. Here the component B is connected to component C via payload modified by A. Now we are considering configuring target variable affects the behavior of existing variables. In enriched data with target variables in Mule runtime, existing variables retain their original values after an operation with their target variable finishes processing. For example, consider a flow where you set variable 1 and 2 and then operation modifies the variable 1 and 2 and also outputs the target variable A. In this case, after the execution of the operation, variable 1 and 2 returns to their previous values. Because the component set a target variable, variable 1 and 2 revert to their previous values after execution of the component. Original payload is connected to set variable 1. Set variable 1 is connected to set variable 2. Set variable 2 is connected to component modified variable 1 and 2, and it is connected to set variable A, and component modified variable 1 and 2 is connected to interacts with original payload and it produces here. Now we are considering architecture in configure shared resources in Mule runtime. A Mule domain project in Anypoint Studio has following key files. The source main mule domain config.xml. This is the shared resource configuration file. This file must have a mule domain config.xml file name. pom.xml. This is the dependencies file descriptor. It is a Maven pom file required plugins for the domain projects. Mule-artifact.json. This file descriptor. This file is a descriptor for domain artifact. Here you can see the consuming REST API flow in Mule runtime. The Mule application consuming REST API consists of the following: one or more message process configured to build your request. An HTTP request operation configured to call REST API, and one or more message processors configured to accept and process the response. Here you can see the consuming REST API flow. You configure the portions of the application that build the request and process the response. Here you can see consume REST API. Here build the request. In listener, the VM listener and transform message are in build the request. Here the listener VM listener is connected to transform message is connected to request is in call the REST API, request is connected to transform message and write are in process the response, and transform message is connected to write. Here you can see what happens when an event processor such as an HTTP request or database operation throws an error. In messaging errors in configure error handlers in Mule runtime, Mule throws an messaging error a mule error whenever a problem occurs within the flow of the mule app, where the mule events and the messages are the messages they contain are processed. You can handle mule messaging errors in more than one way. You can rely on the default error handling mechanism. Within the flow, you can set up on error components, on error continue and on error propagate inside the flow built in error handle component. This component can contain any number of components to process the error. The following here figure shows what happens when an event processor such as an HTTP request or database operations throws an error. Outside the flow, you can set up error handler component and reference it from other error handler configurations. The global error handler can contain on error component and their contents. It is possible to set up error handling from within try scope that reside in the flow. The scope contains a built-in error handler in which you can configure on error components and their contents. Here you can see the flow, and event source is going to the event processor is going to another event processor, and so there's another one here, and there's an error, and then event processor is going to the event processor in on error is connected to the another event processor in on error, and on error is in error handler is and error handler and event source event and other event processors here are in the flow. Here you can see synchronous logging in Mule runtime. By default, Mule logs messages asynchronously. When logging synchronously, the execution of the thread that is processing your message is interrupted to wait for the log message to be fully handled before it can continue. Here you can see thread and you can see here logging, and then let's continue here. Here you can see asynchronous logging in Mule runtime. When logging asynchronous, the logging operation occurs in a separate thread, so that so the message can process before the logging completes. In most situations, Mule recommend that you use asynchronous logging because the substantially improves the throughput and lowers the latency of the message processing. When asynchronous logging is used, some actions might be logged if there is a system crash. The situation occurs because log writing is performed on separate thread that runs independently of other actions. If you use app logs as audit trails, configure your app to always use synchronous logging. This prevents the loss of any log messages. Mule 4 introduced thread local functionality to optimize the memory usage of log4j. To enhance the use of this feature, you can set the system property async logger config ring buffer size. 20,000 is the suggested value, but you need to tune it to meet your needs. Here you can see the thread is going on. This is logging is in the separate thread here. Here you can see performance tests in configure logging in Mule runtime. The chart here shows the performance difference between synchronous and asynchronous logging. How much latency is increased as more concurrent messages were added. In this test, the app logged about 1 million messages. Using an increasingly higher amount of thread on each run, each transaction resulted 1,000 messages. As indicated by the chart, the result of logging asynchronously are significantly closer to the result of asynchronously here. As indicated by the chart, the result of logging asynchronously here are significantly closer to the result of not logging at all. Here you can see the asynchronous logging, here no logging, and here the synchronous logging. Here you can see a reliability pattern couples a reliable acquisition flow with an application logic flow as shown in this diagram in Mule runtime. A reliability pattern is a design that results in a reliable messaging for an application, even if the application receives messages from a non-transactional connector. A reliability pattern couples a reliable acquisition flow with an application logic flow as shown in this diagram. Reliable acquisition flow, the left side of the diagram here, delivers a message reliably to the Mule event source that does not implement the transaction to an outbound operation of a connector that implements the transaction. The operation can be of any type of transactional endpoint such as VM or JMS. Such as if the reliable acquisition flow cannot deliver the message, it ensures that the message isn't lost. The socket-based connections like HTTP, this means returning the unsuccessful response to the client so that the client can retry the request. For resource-based connections like file or FTP, it means not deleting the file so it can be reprocessed. The application logic flow, the right side of the diagram delivers the message from the event source that uses transactional connector to the business logic for the application. Here you can see the request is client is connected to the HTTP via request, and here the HTTP is connected to the client is connected to the receive message via request, and it's HTTP, and receive message is connected to the client via state response, and here the receive message is connected to the add message queue, so the VM, and add message queue is connected to the VM. Receive message and add message queue and are in reliable acquisition flow, and VM is connected to the application, connected to the consume message from queue VM here, and the consume message from queue flow of ref to business logic subflow, and add message queue are in application logic. Here the consume message from queue is connected to the flow ref to the business logic subflow, and it's connected to the add message to queue, and it's connected to the VM. Here the transaction one here. Here you can see a reliability pattern where the reliable acquisition flow delivers a message to a JMS endpoint. You can couple reliable acquisition flow with any type of transactional endpoint. You don't have to use VM endpoint in reliability pattern. The following this diagram illustrates reliability pattern where reliable acquisition flow delivers a message to an JMS endpoint. And also we can use the file-based VM standalone Mule, provided easy to use with Mule. There is no need for additional software. Applies only to non-clustered environment. We can use the we can have a JDBC as endpoint. Depending on the resource available, JDBC can hold a large amount of information. requires additional software. Database server can be complex to use since property DBMS schemas required, and I can use the endpoint as JMS like here. Enable for persistence, applied to both clustered and non-clustered environment, requires additional software. Message queue server. Note the comparison doesn't include any in-memory persistence setup for VM and JMS because they can lose messages that are not considered reliable. Here the client is connected to receive message via request. Receive message is connected to the client via status response. Receive message and add message to queue are in reliable execution 4. Receive message is connected to add message to queue, and it's connected to JMS. JMS is connected to consume message from queue, and it's connected to flow ref to business logic subflow, and it's connected to add message queue. Consume, and it's connected to JMS. Consume message queue, ref to business logic subflow, and add message to queue in application logic flow transaction 1. Here you can see performance test invoice structure. In separate host avoid interference in Mule runtime. Here is used a control environment. Use a self-control environment to obtain repeatable, reliable and consistent data. Use an infrastructure made by Triplet. Use a dedicated host for Mule application to isolate the app information, preventing other running processes from interfering the result in the case of on-premises test. Use separate dedicated host for running load client tools that can drive the load without becoming a bottleneck. Use separate dedicated host on to run backend services like database, Tomcat, JMS, ActiveMQ, and so on. Test using the same host that the application uses in production. For the on-premises test, run the load client runtime server and backend in the same Anypoint virtual private cloud, Anypoint VPC to decrease the network latency. For Cloud Hub test, run the load client and backend server on dedicated machine that is separate from but in the same region as the Cloud Hub worker to decrease the network latency. Use a wired stable network. Don't use your laptop because it may outperform the same application deployed to a customer's environment, particularly if it is virtualized. Here you can see the performance test infrastructure here. Here you can see a load client, Apache JMeter, Gatling, Apache Benchine load client, and load client is connected to Mule. Mule is connected to a backend. Here MySQL, Apache, RabbitMQ, JMS in backend. Now we are considering Mule high availability in cluster runtime instances. In Mule runtime, the enterprise edition, Mule high availability provide basic failover capability for Mule. When the primary Mule instance become unavailable, for example, because of a fatal JVM or hardware failure, or it's taken offline for maintenance, backup instance immediately become primary node and resumes the processing where failed instance left off. After system administrator has recovered the failed Mule instance and brought it back, the online automatically becomes the backup node. The seamless failover is made possible by the distributed memory store that shares all transient state information among clustered Mule instances such as SCADA service event queues. in-memory message queues. Mule high availability is currently available for following transports: HTTP including CFX web services, JMS, WebSpare MQ, JDBC, file FTP, clustered replaces local VM transport. Mule high availability is available with Mule enterprise subscriptions. Here the web portal or REST and web services .NET or HTTP and applications are connected to reverse proxy server, and reverse proxy server is connected to Mule active here. Mule active interacts with Mule passive here, and JMS database and file FTP and SFTP are connected to Mule active here. Here you can see JMS queues in cluster runtime instances in Mule runtime. JMS can be used to archive HA and FT by routing messages through JMS queues. In this case, each message is routed through JMS queue whenever it moves from component to component. Pros easy to do, well understood by developers. Cons require a lot of transactions, and transaction can be complicated. Performance hit if you are using XA. Here you can see the Mule server in a cluster, and transport is connected to inbound router via external queue, and inbound route is connected to service component via external queues, and service component is connected to outbound router via external queues, and outbound route is connected to transport via external queues. Here you can see the example in load balancers. In cluster runtime instances in Mule runtime, load balancers simply route requests to different servers based on the current load of each server and which servers are currently up. Load balancers can be a software or hardware based. This approach commonly used in clustered databases. Pros straightforward to do, well understood by developers, and cons not a complete solution on its own, doesn't provide fault tolerance. In this example architecture, HTTP requests come through a load balancer and are immediately put on a JMS queue. JMS queue is clustered between different servers. A server will start processing a message of the JMS queue and wrap everything in a transaction. If the server goes down, a transaction will roll back and another server will pick up the message and start processing. Note the HTTP connection is open for duration of this process. This approach will not work as load balancer will not transparently switch connections between servers. In this case, HTTP client will need to retry the request. Here the HTTP with load balance is connected to cluster JMS queue, and it interacts with the transaction, and server 1 and server 2 are within the transaction here. Now we are considering handling stateful components in cluster runtime instances in Mule runtime. While most applications can be supported by different techniques, some require sharing state between JVMs more deeply. One common example of this is an aggregator component. For example, assume you have aggregator that is aggregating messages from two different producers, producer 1, and send the message to the aggregator, which received it and hold it in the memory until producer 2 sends the message. If the server with the aggregator doesn't goes down between between producer 1 sending a message and producer 2 sending a message, producer 2 can't just send the message to the different server because that server will not have the message from producer 1. Solution is to this is to share the state of the aggregator component across different machines through clustering software as Terracotta, Oracle Coherence, JGroups, etc. By using one of these tools, producer 2 can simply fail over to a different server. Note that the MuleSoft has not tested Mule with these tools and does not officially support them. Pros works for all clustering cases, can work as a cache as well. Cons not officially supported by MuleSoft, required performance tuning to get things work efficiently. Here producer 1 and producer 2, number 2 is connected to aggregator is connected to some other component. Here you can see a Mule runtime high availability HA cluster overview in cluster runtime instances in Mule runtime. Important for an equivalent to clustering in Cloud Hub. See the Cloud Hub HA in the documentation for details about how workers can be shared or doubled to scale your application and provide high availability. Mule Enterprise Edition supports scalable clustering to provide high availability HA for applications. A cluster is a set of Mule runtime engines that act as a unit. In other words, a cluster is a virtual server composed of multiple nodes, Mule runtime engines. The nodes in a cluster communicate and share information through a distributed shared memory grid. This means that data is replicated across memory in different machines. Incoming messages, here the outgoing messages. Here the nodes distributed shared memory interacts with nodes. Distributed shared memory and cluster nodes are in cluster. Cluster has incoming messages and outgoing messages. Contact your service representative about pricing of this feature. Here you can see the node 1 processes message 1 while node 2 simultaneously process message 2. In benefits of clustering in cluster runtime instances in Mule runtime. By default, clustering Mule runtime engines ensures higher system availability. If a Mule runtime engine not becomes unavailable due to failure or planned downtime, another Mule in the cluster can assume the workload and continue to process existing event and messages. Following figure illustrates the processing of incoming messages by a cluster of 2 nodes. Notice that the processing load is balanced across the nodes. Node 1 processes the message 1, and node 2 processes while node 2 simultaneously processes the message 2. Here you can see the client, and client is connected to the cluster via message 3 and 4 here. While the node 1 processes message 1 and node 2 processes message 2 here. Node 1 and node 2 are in cluster here. Here you can see the if node 1 process if node 2 fails, node 1 processes both message 1 and 2. If not in benefits of clustering in runtime cluster runtime instances in Mule runtime, if node 1 fails, the other available nodes pick up the work of the failing node. As shown in the following figure here, if node 2 fails, node 1 processes both message 1 and message 2. Here client is connected to the cluster via message 3 and message 4, while message 1 and 2 when node 1 is processing message 1 and 2, and node 2 is failed here, and node 1 and node 2 are in the cluster here. Here you can see Mule runtime HA clustering, how the workload sharing in more details in cluster runtime instances in Mule runtime. Because all nodes in the cluster of Mule runtime engines process messages simultaneously. Clusters can also improve performance and scalability. Compared to a single node instance, clusters can support more users, so improve application performance by sharing their workload across multiple nodes or by adding nodes to the cluster. Following figure illustrate the workload sharing in more details. Both nodes process messages related to order fulfillment. However, when one node is heavily loaded, it can move the processing for one or more steps in the process to another node. Here, processing of the process order discount step is moved to node 1, and the processing of fulfill order step is moved to node 2. Beyond benefit of such as high availability through automatic failover, improved performance and enhanced scalability, clustering Mule runtime engines offer the following benefits. Beyond automatic coordination of access to resources such as files, databases, and FTP resources, the Mule runtime engine cluster automatically manages which Mule runtime engine will handle communication from the data source. Automatic load balancing of processing within a cluster. If you drive your flows into a series of steps and connect these steps with a connector such as VM, each step is put in a queue, making it cluster enabled. The cluster of Mule runtime engines can then process each step in any node to better balance the load across nodes. Raised alert, you can set up an alert to appear when a node goes down and when the nodes come back up. Not all Mule runtime engines in a cluster activity process messages. Note that each Mule node is internally scalable. A single node can scale by taking advantage of Mule cores. Mule operates as a single node in a cluster even when it uses multiple cores. Here you can see the message 1 path of the message 1. Here you can see the path of the message 2. Here the message 1 is connected to receive order. Order is connected to process order discount, and process order discount is connected to fulfill order. Here the message 2 is connected to receive order, and my receive order is connected to process order discount, and process order discount is connected to fulfill order. Here the receive order, process order discount, and fulfill order in the node 1. Here receive order, process order discount, and fulfill order are in node 2. Here node 1 and node 2 are in the cluster. Here you can see the cluster design and management. In cluster runtime instances in Mule runtime. Anypoint runtime manager enables you to set up a cluster of Mule instances and then deploy an application to run on the cluster. You can also monitor the status information for clusters and individual nodes. When clustered, you can easily manage several servers as well. Mule cluster consists of 2 or more Mule runtime engines or nodes grouped together and treated as a single unit. With the initial configuration, MuleSoft recommends that you scale a cluster to more than 8 Mule runtime engines. With the Anypoint runtime manager, you can deploy, monitor, or stop all the Mule runtime engines in a cluster as they are in a single Mule runtime engine. All the nodes in a cluster share memory as illustrated below here. Mule users an active model to cluster Mule runtime engines. The benefit of this model over an active passive approach is that your Mule application run in all nodes, splitting message processing with other nodes in the cluster, which expedites the processing. Here incoming messages are connected to a node 4 cluster here. Here the nodes and shared memory are inside the cluster. Here node 1, node 2, node 3 and node node 1, node 2, node 3 and node 4 are interacting with shared memory here. Here the 4 node cluster is connected to outgoing messages. Now we are considering here the cluster can potentially process a single message on multiple nodes as it passes through a VM points in the application flow as illustrated here. In queues in cluster runtime instances in Mule runtime, you can set up a VM queue explicitly to load balance across multiple runtime engines nodes. Thus, if your entire application flow contains sequence of child flows, the cluster can potentially process a single message on a single child flow to whichever Mule runtime engine happens to be available at the time. The cluster can potentially process single message on multiple nodes as it passes through VM endpoints in the application flow as illustrated here. Here you can see the Mule application deployed to 4-node Mule cluster. Here flow this interaction with flow A. Flow A is connected to flow B async. Flow B is connected to flow C async, and flow C is connected to flow D async, and flow D is connected to flow A. Here the flow node Mule cluster designed for load balancing across nodes. Here the node number 1 available, and it's connected to node 2 number 2 available, and it's connected to node 4 4 available, and it's connected to node number 3 available. Other nodes are BC here, and here these nodes are in the cluster. Now here you can see the deploying Mule for HA and DR strategies in cluster runtime instances in Mule runtime. You can deploy the Mule runtime in many different topologies to address your HA or DR strategies. One method is through the use of clustering, which is described. One method is use of clustering. Mule high availability clustering provides the basic failover capability for Mule. When the primary Mule runtime becomes unavailable, for example, of a fatal JVM or hardware failure, or it is taken offline for maintenance, the backup Mule runtime engine immediately becomes the primary node and resumes processing where the failed instance left off. After a system administrator recovers the failed Mule runtime server and puts it back online, that server automatically becomes the backup node. Seamless failover is made possible by distributed store that distributed memory store that shares all transient state information among clustered Mule runtimes, such as SCADA, service event queues and in-memory message queues. As you build your Mule application, it is important to think critically about how best to architect your application to achieve the desired availability, fault tolerance, and performance characteristics. Here the incoming messages are passed to cluster. Here the Mule and distributed shared memories are in the cluster, and distributed shared memory mules are connected to mules interacts with the distributed shared memory. Mule and distributed shared memory are in the cluster, and cluster is outputting outgoing messages. Here you can see cold standby in high availability options in cluster runtime instances in Mule runtime. The Mule environment is installed and configured, however one or more operating systems are not running. This can be a backup of a production system or virtual machine. The environment of the operating system plus the Mule runtime has been started after an outage is detected. Downtime sum the time it takes to start the environment and direct traffic. Here this running one, and here the down one. Here you can see the worm standby in high availability options in cluster runtime instances in Mule runtime. The Mule environment is installed and configured, however the Mule runtimes are not running. Only the operating systems Mule runtime is started after an outage is detected. Downtime a little, the time it takes for the Mule runtimes to start and to route traffic to the environment. Here it's running, and here the Mule is down here. Now we are considering hot standby, active, passive. The Mule environment is installed and configured and fully running. However, it's not processing request until an outage is detected. Downtime minimal to none. Time to route traffic to an environment. Here you can see it's running here. Here you can see active model. Active in high availability options in cluster and down runtime instances in Mule runtime. The load balance clustering environments, there are 2 or more Mule environments, and each environment has its own cluster that are fully operational. The load balancer is directing traffic to all of the environments. There is no service downtime, and downtime is none. There is no service downtime. Here you can see the load balancer is connected to the Mule and OS here. Mule and OS interacts with the Mule and OS here, and the here you can see the Mule and OSs are in the cluster here and in the cluster here. Here the load balancer, load balanced single clustered environment. There are 2 or more Mule environments. However, they are part of the same clustered environment. To achieve this scenario, the network latency between the environments must be less than 10 milliseconds. Downtime none. There is no service downtime. Here load balance is connected to the Mule environment, 2 Mule environments. Mule environments are in the and the OS are in the cluster here. Here you can see the active clustering deployment model in high availability deployment models in cluster downtime runtime instances in Mule runtime. It is possible that 2 nodes in a clustered or load balanced environment can support 1500 TPS with the 1 second responses. In this state, the normal operation of the SLA is being met. If a node fails, the service is impacted. However, the impact does not breach the SLA because the node is able to handle 700 TPS with 1 second responses, well above the agreed upon the accepted impact level. Distribute the load evenly among the multiple Mule nodes. All nodes have the same capabilities. All nodes are active at the same time. Cost vary depending on the SLA requirements. This model needs 2 nodes to satisfy SLA. If the SLA acceptable service impact changes to the terms stated in the normal operations, and then at the minimum the environment will need 3 nodes to accommodate 1 node failure. More nodes may require depending on the probability of not having the last 2 nodes running. Here the consumer interacts with the load balancer. Load balancer interacts with the mules here, and mules and the OS are in the cluster here. Now here you can see active clustering fault tolerance deployment model in high availability deployment models. The basic definition of fault tolerance is a failure within the system does not impact the service at all. This differs from the high availability as service impact and downtime is tolerated. Fault tolerance differs from the high availability by providing additional resources that allow an application to continue functioning after component failure without interruption. Fault tolerance environments are more costly than high available environments. The degree of fault tolerance requires the probability of the system failures. Take the SLA example highlighted under the high availability and makes the minimal acceptable service impact level match the normal operation requirements. The new overall SLA now requires the system to be able to handle 1000 transactions per second with 1 sec response times, 0 downtime, and 0 service impact time. Zero service impact. It is if the probability of having more than one node fails is low, then the architecture would simply require 3 nodes. However, the probability of probability of more than one node is higher than acceptable. More than 3 nodes are required to accommodate the multiple failures here. More costly due to required redundant in order to meet the defined SLA. Here consume interacts with the load balancer, load balance interacts with the mules here, and here's this mule is fails, and here the redundant replacement node here, and here you can see the nodes are in the cluster, and here you can see the zero downtime deployment model. The zero downtime deployment model in high availability deployment models in cluster runtime instances in Mule runtime. The goal is to be able to quickly make changes to the environment without impacting SLAs, including upgrading infrastructure and applications running on the infrastructure. Typically, zero downtime deployments leverage a side-by-side deployment where the old and new coexist for a short period of time. This is in contrast to an in-place deployment where the service may experience reduced capacity to complete downtime. Gartner defined the continuous operations as those characteristics of data processing system that reduce to eliminate the need for planned downtime, such as scheduled maintenance. One element of 24-hour a day, 7-day a week operation. Baseline production environment is the current operating system. A new environment is created with the changes, upgraded times, configuration, new application, etc. A small percentage of traffic flows to the new environment and creates as the confidence in the new environment increases. Baseline production environment continues its use until the new environment is fully operational. It is handling 100% of the traffic. Once the new environment is accepting all traffic, it becomes a new baseline production environment. Environment and the previous baseline production environment terminates. This example below here, this is assuming that each environment is using the same number of Mule runtimes and cores. It is possible that the new environment may have more or less number than the baseline environment. Here the deployment step. Here the new production environment deployed, and a small percentage of traffic is routed to the new environment. Here the consume is connected to the router, and router is connected to here 94 route considered here this baseline production current environment via 90% of traffic. You can see the mule here, and here the route is connected to a new production environment via 5% of the traffic here. The mule and OS are here. In the deployment step, the confidence in the new environments continues to increase and more traffic is routed to it. Here the confidence of the environment is continuous and continues to increase and more traffic is routed to here. Here the consume interacts with the router. Here the router is connected with baseline production current environment with 5% of the traffic, and here the route is connected to the new production environment with 95% of the traffic. And here the after traffic has been routed to the new environment, here the after traffic has routed to the new environment. Here the route is connected to baseline production current environment with 0% of traffic, and here the route is connected to the new production environment with 100% of traffic. All traffic has been routed to the new environment, which has been promoted to the baseline production environment. The previous baseline environment has been terminated. Here you can see the consumer interacts with the router. Route interacts with the new baseline production current environment with 100% of traffic, and there's no the connection is terminated with the between router and the new baseline production with the baseline production current environment. The cost, this deployment method may temporarily add capacity to service, can be a few minutes, hours, or days. Here you can see a Mule event and message. The MuleSoft in Mule runtime, MuleSoft includes a simplified Mule message model in which each Mule event has a message and associated variables. A Mule message is composed of the payload and its attributes, metadata such as file size, variables was which hold that arbitrary use information such as operation results, auxiliary values, so on. In general, operations do not automatically propagate variables to other components like a listener. If you use the flow reference component, it does not propagate variables within flows. This is simplified message model makes it easier to work with data in a consistent way across connectors without overwriting information. Here you can see the Mule event and the message. Here you can see the Mule flow. Here the variables and Mule message are in Mule event, and attributes and payloads are in Mule message. Here you can see to use a new API instance for configuring an independent Mule runtime instance on MuleSoft. In migrate using a new API instance, in migrating API gateways in Mule runtime. To use a high-level proposal illustrated in this diagram, to use a new API instance for configuring an independent Mule runtime instance on MuleSoft here. If your Mule application is not a proxy, the same proposal applies to your migration procedure without backend component. To migrate your Mule 3 API to MuleSoft using new API instance, from the API administration page in API manager, select API, then create new API. Use an instance label to identify this new API instance. On the endpoint configuration window, select MuleSoft in Mule version and save. In the left navigation pane in the API manager, apply alerts, SLA tiers and policies to your API. If your API uses contract-based policies, for example, client ID, enforcement policy, migrate the contract of the API instance. If you completed configuring your API, start your MuleSoft application and try sending it request. After successfully validating your application, undeploy your Mule 3 application. Here you can see API manager. Here the audit log instance A and audit log instance B are in API manager. Here the API manager interacts with Mule 3 proxy, and here the API manager interacts with the MuleSoft proxy via connects to an instance. Here the load balancer is currently load balancer is connected to Mule 3 and Mule 3 proxy, and Mule 3 proxy is connected to backend. Here the load balancer is connected to MuleSoft, and MuleSoft proxy is connected to the backend. Here you can see Mule message structure in Mule runtime. Here we examine the Mule message in the context of the flow rather than a batch job. If you please see batch processing in the documentation for more information about how messages in the batch jobs are broken up and processed as records. The Mule message is the data that passes through an application via one or more flows. It consists of two main parts: the message header, which contains the metadata about the message, the message payload, which contains the your business specific data. A Mule message is itself embedded within the Mule message object. Some Mule message objects may contain variables, attachments, and exception payloads. However, as attachments and exception payloads are not frequently used or manipulated, this overview does not include the details about much about them here. Here the tip: if you have ever in doubt about the structure of the message in a given step of the flow, you can easily check by using the Data Science Explorer. Here the inbound property and outbound property are in the in header. Payload and header are in message. Attachment variable and exception payload are in the message object. Here you can see the inbound properties. The inbound properties the inbound properties are immutable, are automatically generated by the message source and cannot be set or manipulated by the user. They contain metadata specific to the message source that prevents scrambling of data formats or other processing mishaps later in the message lifecycle. A message retains its inbound properties only for the duration of the flow. When the message passes out the flow, its inbound properties do not follow. See the image here. Here the inbound property prop1 is equal red is in the header and payload is in the message and message is in the message source, and the message source is connected to the next message connected to the message processor. Here the inbound property prop equal red and is in the header and payload is in the message and message is in the message processor, and message source and message processor are in the flow A here. Here the message processor is connected to the message source in flow B. Here the header is in the message and payload is in the header and the payload is in the message and message is in the message source and message source is connected to the message processor. Here the header is in the header and the payload are in the message and message is in the message processor. Here the message source and message processor is in the flow B here. Here you can see the outbound properties. Outbound properties are mutable. They are set during the course of a flow and can become inbound properties when the message passes from the outbound endpoint of one flow to the inbound endpoint of the different flow via transport. They contain metadata similar to that of the inbound property, but an outbound property is applied after message entered the flow. Outbound properties can be set automatically by Mule, or a user can set them by manually inserting one or more transformer and elements in the flow. Note that if the message is passed to a new flow via flow ref rather than a connect, the outbound properties remain outbound properties rather than being converted into inbound properties. See the image here. Variables are defined metadata about the message. Variables have three scopes. Flow variables apply only to the flow in which they exist. Session variables apply across all flows within the same application. Record variables apply only to record process as part of a batch. Here the header is header and payload are in the message and message in the message source. Message source is connected to message processor. Here the outbound property prop1 equal blue is in the header and payload are in the message and message is in the message processor here. message source and message processor is in the flow A. Here the message process is connected to the message source here in the flow B. Here the inbound property prop1 equal blue here, and it's in the header, and header and payload is in the message, and message is in the message source, and message source is connected to the message processor. Here the inbound property prop1 equal blue, and it's in the header, and the header and payload is in the message, and message is in the message processor. Here the message source and message processor are in the flow B here. Here you can here you can see what is ESB, and here the ESB is there, and request service request is connected to ESB, and here service provider is connected to ESB. Here you can see point-to-point connection. Here the S1 is connected to S2, S3, and S4. Here S2 is connected to S1, S3, and S4. Here the S3 is connected to S1, S2, and S4, and S4 is connected to S2, S3, and S3 and S1. You can see ESB architecture. Here you can see the enterprise service bus, and messaging systems is connected to enterprise service bus. Here service bus is connected to legacy system mainframes are connected to service bus. Here here you can see the web services through web services. Here the web service connected to enterprise service bus via web services, and here the media service connected to enterprise service bus via web services, and here the e-commerce is connected to ESB via web services, and the mobile DNS set is connected to ESB via web services. Here the legacy system mainframes are connected to ESB via web services, and here the mail server is connected to ESB via web services, and here the data bank is connected to ESB via web services, and here the FTP service connected to ESB via web services, and here the service connected to ESB via web services, and here the messaging systems are connected to ESB via web services. Here you can see the ESB, and ESB is a basically integration of a new and old new and the old, providing a central place for services, applications, and services, applications, and IT resources in general that you want to connect. Here you can see the enterprise service bus, a reliable, asynchronous, secure messaging here, and here the JMS here. So in the here the reliable, essential, secure messaging, and JMS is inside in enterprise service bus. Here the ERP interacts with ESB via transformation SLT and JCA. Here the .NET interacts with enterprise service bus via SOAP and HTTP. Here the web services interacts with the ESB via SOAP and HTTP. Here the C and C or C++ legacy application interacts with the ESB via SOAP or HTTP. Here J2E interacts with the ESB via JMS. Here you can see microservice architecture versus legacy monolithic architecture. Microservice architecture versus a legacy monolithic architecture is an approach to developing software application as a series of small services, each running autonomously and communicating each other. For example, through HTTP requests to their APIs. Microservices have called it into question the future of ESB But how does the new architecture trend really affect enterprise service bus? It seems that microservice has arrived to stay. More and more CEOs want to install this type of architecture in their projects. Microservices are perceived as a future of doing business. Many believe it is a general change promoted by digital transformation and think that ESB is becoming obsolete. Are they right? Are microservices the new era of SOA? Definitely, you have to take them into account. But for ESBs, no, they are still available, still alive. We must adopt our concept of this we must adapt our concept of this architecture and can no longer understand the integration bus as a centralized and inflexible concrete structure for the whole company. When we talk about them today, we should think flexible, scalable, and well distributed infrastructure in which we can incorporate, implement, and monitor any type of service in an agile and efficient way. The ESB must fulfill a function of integration, coordination, routing, and monitoring of business activity. Understanding ESB is in this way we can build application through services and microservices to solve the requirement and needs of the company. The services must be treated in the individualized way with the standard interface to a platform with automatically scalable execution time. Thus, these services are decoupled and scaled in a linear fashion on non-specialized hardware. This is the best way to understand enterprise service bus today. Microservices do not mean the death of ESB if the latter is used to be suitable way. That is to stay a focus on the architecture where services are protagonist and not in the centralized architecture towards the integration bus itself. About this here you can see a monolithic application puts all its functionality into a single process and scales by replicating the monolithic monolith on multiple servers. Here the microservice architecture puts each element of the functionality into a separate service and scales by distributing these services across servers, replicating as needed. Here you can see a MuleSoft architecture. The Mule plays a special role as it is not a full JBI implementation but only provides external JBI connectors which can be used to integrate with other JBI environments like service mix. It is also not a typical ESB as is often stated. For example, in because it does not provide common messaging backbone as an associated back-end services, but more of a freely combinable mediation layer where components are not plugged in but stick together as needed. This is seen as an advantage over traditional ESB, stating one difference between Mule and traditional ESB is that Mule only converts data as needed. With typical ESB, you have to create an adapter for every application you connect to the bus and convert application data into single common messaging format. Mule increases the performance and reduces the development time over traditional ESB. As a result, Mule uses a proprietary API and message format and does not embrace JBI or SCA as its underlying integration model. Service components, previously called Universal Mule Objects or UMO, implements custom application logic can operate on the content of the message on a logical level. Similar to JBI service engines, they are decoupled from specific messaging or protocol formats required for communicating with other components or external applications. This is performed by transformers, which converts between different data formats and wrap them in Mule messages, whereas the transport handle protocol conversions as needed, bridging between communication protocols such as JMS, SOAP, HTTP file or proprietary protocol similar to JBI binding components. Finally, routers are used to deliver incoming messages to service component and for sending outgoing messages to the target component according to the configuration. In JBI, there is a central shared router that handles messaging the messaging and connection in all endpoints. The normalized message router routers can perform additional logic such as filtering or message composition or decomposition, implementing a message routing patterns. The basic architecture and message flow is illustrated in this figure here. Mule uses a compact XML format for describing the configuration and these are the inbound and outbound routers. The Mule uses XML-based XML format for describing the configuration and supports the Spring for lightweight specification of the desired integration. Development support is provided via the Ant and Maven scripts. There is an also Eclipse plugin, Mule IDE, for basic configuration and deployment from which within the IDE. Recently, the Mule IDE has been extended to provide visual editor for designing integration maps, but this has not yet been ported to the Mule, the new Mule 2.0 release. Compared to the full JBI solution, Mule is easier to get started with the and provides a more lightweight configuration-centric integration model with little restrictions on architecture or message format. Components may have be simple Java object or Spring Beans, which can be directly integrated without code changes by writing suitable configuration. This simple approach allows to quickly set up the prototypes and reduce the time to market or for small to medium size projects, but allows solution to grow enterprise scale when needed. Because of the clustering support in Mule, especially in the small or performance critical settings, Mule provides an advantage by transforming messages only when it is needed at the last possible moment, which is sometimes compared to late binding in programming languages. Mule has recently been integrated into an integration stack with various components working together called Mule Gateway. Integration into existing environments is possible in several ways, either as a component inside JWA application server or by connecting to an existing message bus over JMS or similar protocol supported by Mule. The deviation from Open API's common messaging format and core ESB principles also has significant disadvantages and bears the danger of vendor lock-in. Mule is the only implementation available, and spaghetti integration as components are still tightly coupled and statically configured, which can result in high complex and transports. In this way, Mule really only relies component integration and not service-oriented integration, which would require the consistent usage of standard-based interfaces such as WSDL, which is utilized in JBI. Also, because the endpoint have to explicitly specify, there is no real location transparency, which is the core principle behind SOA. Moreover, Mule does not support hot deployment or reconfiguration on the fly. This has been the long-standing point of criticism and will be addressed in upcoming version by using OSGI as underlying component model. Much of the Mule's unique advantages proclaimed in Mule's advantages are there and can be realized with JBI in the standard compliant manner without incurring disadvantage of Mule, as shown here. any component type is supported in JBI. Components can be easily wrapped into service engineer or engines or binding components. Service mix also support POJO, plain old Java objects, directly through API extensions and provide lightweight configuration model using Xbeans. JBI 2.0 will also support OSGI components. Better component reuse and less API overhead. JBI components can be reused across different runtimes, which is out of scope for Mule. This comes at the price of the added API complexity, which is why the many JBI implementation introduce more lightweight API layers that allow easy development of JBI component, but are not always fully JBI compatible, restricting use across JBI containers. JBI 2.0 will, however, refactor the API. It is overly complex or restrictive and make the specification more developer friendly in general. Recording is also not necessarily in JBI, as service units provide rich ways of reconfiguration even at runtime. No restriction on the message format. JBI requires transformation into normalized but non-canonical XML format on the purpose, and its distributed complexity of the integration solution minimizes the risk at tight coupling and point-to-point integration, which can easily happen at the Mule implementation. Are free to optimize flow where possible, so transformation is not performed when the communication endpoints use the same protocol. Also, binary formats and property extensions are supported all through attachment and metadata respectively. Support for various topologies beside ESB. The JBI specification does not restrict implementation to an ESB topology, but allows the implementation to choose any topology that makes sense in the target environment, which has been already shown target environment. And next version of OpenESB will support peer-to-peer messaging using JXTA, and other JBI implementations support various messaging and clustering forms such as JMS, SEDA, and proxying. The disadvantages identified above and restriction imposed by the proprietary Mule API make it unusable for sustainable tool integration, especially when comparing against the requirement and alternatives outlined before. Also, Mule 1.x has been previously tried for the toolnet redesign in a case study, but was found to be too restrictive with regards to endpoint addresses, as it did not support dynamic endpoint. For example, when tools come online or go offline, this limitation to static configuration impedes dynamic tool reconfiguration and agile workflows. Mule does not fully apply best practices in SOI and enterprise integration, which may result in complex solutions that are easy to build initially but hard to maintain later. However, this straightforward approach to integration, easy configuration, maximizing reuse of existing service component, and low API overhead, maximizing performance and ease in development, are the key advantage that should be allowed in JBI 2.0 where possible. Here you can see a message sent to http:// here myfirm.com/mule, and it's interacts with the HTTP message here, and it's connected to HTTP transport, and HTTP transport is connected to the service here. Here you can see the inbound router, and here the endpoint http://myfirm.com/mule is there, and here the outbound route is connected to the endpoint JMS ://myq. Here the customer data service component, data service component and endpoints are in the service here, and here the service is connected to JMS transport, and the transport is connected to JMS message here, and it's connected to service here. Here you can see the inbound router and endpoint JMS ://myq, and here the order fulfillment service component, and this endpoint are in the service here. Here you can see Mule ESB service framework. The service framework in Mule has existed for building integration solution. Design is simple and highly scalable. The message flow in the channel to an inbound endpoint, to the transformations and filters are applied if necessary. The service component processes the messages, and finally for the outbound router, send them to their way to the desired outbound endpoint. Again, applying the transformations or filters as necessary. Using the basic concept, many integration patterns can be solved, and since it is based on SCADA architecture, when processing its asynchronous Mule engines, Mule ensures high performance and scalability. Here you can see the Mule ESB service framework. Mule's service framework. Suddenly the Mule 3 trots along, and you hear about this new concept called flows. Why change your deployments to use the new and what seemed like a different framework? First of all, good news, and if you are existing implementation based on the services, nothing has to change when moving to Mule 3. Services are still valid patterns for implementing integration solutions in Mule, and your application will run and scale just to fine on Mule 3. In fact, we will here you can see application is connected to endpoint via channel here. Here the inbound routers, service component, and outbound routers are in service. Here the endpoints are in the inbound routers, and endpoint interacts with the transformers. And here the inbound routers are connected to service component. Service component is connected to outbound routers here, and here the transformers endpoints are in the outbound routers, and transformers interact with the endpoints, and endpoints are connected to application here via channel. Here you can see an example of Mule flow. In taking to Mule users and reviewing numerous Mule implementation, we discovered that the many implemented patterns that just didn't fit the clean it into a strict service-based framework. They are not simply wrapping a single component with endpoints to decouple it from the protocols and routing requirements. Often they were performing service mediation and light process orchestration, attempting to automate business process, or replace a point-to-point integration solution with a more decoupled mechanism that can be reused or changed as systems or business needs change. Some common use cases that Flow is well suited for include simple integration tasks, scheduled data processing, connecting cloud and on-premises application, event processing where multiple services needed to decouple. When we implement the new message processor in architecture in Mule 3, this allows us to offer new patterns to implement service mediation and orchestration in Studio. You even can see the visual representation of the flow. Most of the use cases supported with services continue to be supported in Flow, along with many new ones based on the Flow specific routers we are implementing. Some key advantages of Flow: create and reuse subflows, chain together multiple components in one flow, integrate endpoints or cloud connectors anywhere in the flow. Here you can see HTTP request is connected to CXF SOAP, and CXF SOAP is connected to create summary, and create summary is connected to here. And here the choice is connected to small load, medium mode, and large load, and it's connected to async. Echo is connected to create tweet, and create tweet is connected to Twitter, and here the echo, create tweet, and Twitter are in async. Here this is connected to SOAP, and SOAP is connected to response. Echo is in the response, and response is connected to here the HTTP. It's about as an example, we can consider these steps. This is about deploy an application from runtime manager. Here, to deploy from runtime manager to Cloud Hub, step 1, sign in to Anypoint platform. Step 2, select runtime manager. Step 3, in the application page, click deploy application. Step 4, provide a name for your application. Step 5, in the deployment target menu, select Cloud Hub if it is not already selected. Step 6, specify the application file. Import a file from Exchange. Click choose file, then import file from Exchange. Select application for the type, then enter the name of your application in the search box. Select the application to deploy, select a version from the version menu and then click select. Next point, upload an application archive, zip or jar file. Select choose file, upload file. Select the file to upload and then click open. The application file size limit is 200 MB. Next point, copy an application from a non-production environment. Step 7, click tabs to configure application options. Step 8, click deploy application. Here you can see the step 3 in the application page. Click deploy application. This is the deploy application page. You can this screenshot shows one here, the application name field, to the choose file menu, and 3, the deploy application button on the deploy application page. As an example 2, we can consider this code segment. This is Cloud Hub Connector 1.0 Mule 4. This is a minimum Cloud Hub configuration. The Anypoint Cloud Hub connector for Cloud Hub connector enables you to connect to a Cloud Hub API from your Mule application. The basic Cloud Hub configuration has following properties: username, the user of the Anypoint platform account, password, the password of the given user, and the environment, the Cloud Hub environment used by default. This is the environment defined as the default Anypoint platform. As an example 3, we can consider this Cloud Hub API example. This following example shows how to retrieve schedules for an application. The Cloud Hub API, the Cloud Hub public API allows you to deploy and manage application in Cloud Hub. You can deploy your application manage schedules and queries within an application, and view logs pertain to an application. You can also view memory and CPU usage and get statistics about Mule messages sent using application. This is the request. And this is the response. As an example 4, we can consider this code segment. Following is an introduction to configuring Mule ESB via the Spring XML file. Following is an example of a simple Mule configuration file. A Mule ESP configuration file is a tree. Each of these elements provide access to configuration objects within Mule. Custom message processors observe a message or modify either a message or a message flow. Example include transformers and filters. Flows use message processors to define message flow between source and target. Mule global configuration, global settings such as default transaction timeout that apply to the entire Mule configuration. Connectors, non-default configuration of any transports use. Endpoints, define the channel and address or path where messages are sent or received. You can define them globally and use them in multiple flows. Transformers convert data from one format to another. You can define them globally and use them in multiple flows. Filters filter out the messages that don't match specific criteria. You can define them globally and use them in multiple flows. And other more advanced things you may configure at this level is security manager authenticates requests based on one or more security providers. Agents are typically used for cross-cutting concerns such as logging or management. Notification allow you to be notified upon certain lifecycle events. Transaction management, Mule transactions are configured in inbound on inbound endpoints, or where an endpoint can be configured to start a new transaction or join existing one. Properties, property placeholders, message property, system, and system properties. There are configurations in Mule configurations are set when Mule context is created. The object becomes immutable after it is started and can be accessed using following, like here get configuration. Interface Mule configuration info, which can be set when creating the Mule context, but becomes immutable after startup. this this is in package org.mule.api.config, and this is implement mule context aware to have the reference injected. Considering login to Anypoint platform from IDE, here we are considering in Anypoint code builder. Here we are considering logging from the IDE through the status bar. The status bar in the desktop and cloud IDE shows your logging status. Not logged into Anypoint platform indicates that you must log in to perform tasks that require a connection to Anypoint platform. You can log in by clicking the notification and following the prompt to log in. The link to your username indicates that you logged in. You can log out by clicking the username and following the prompts. Now we are considering login to the login from the IDE through the command palette. In logging to Anypoint platform from IDE in Anypoint platform builder, you can use the command palette to log in to the Anypoint platform. To log in to the from the IDE to the command palette, open the command palette. Show me how. Select the following command: the MuleSoft login to Anypoint platform. Tip: you can log in and use the filter in the result to select command you want. Then 3 to select allow when prompted to sign in to the platform. Alter login. After logging you in Anypoint platform display, you can close this page now message. To verify your login, ensure username replaces the not login into the Anypoint platform. Now we are considering install the core package and default plugins in installing Anypoint CLI 4.x in Anypoint CLI. Run the following command to install the Anypoint CLI core package and all the default plugins. Here npm install -d -g Anypoint CLI v4. Now we are considering account user described in Anypoint platform accounts in Anypoint CLI 4.x list of command in Anypoint CLI. Account user describe flags returns your account information including your username, your full name, and your email address and creation date of your account. Use the --output flag to specify the response format. Supported values are table, default, and JSON. This command accepts the default flag --help. Now we are considering a summary of changes in Anypoint integration, Anypoint platform integration overview in RPA. After your organization is integrated into the Anypoint platform, users log in to RPA Manager, RPA Builder, and RPA Recorder using their Anypoint platform account. Administrators configure RPA users, teams, and permissions using access management instead of user management module in RPA Manager. RPA Manager duplicates roles and user groups and start using teams from the Anypoint platform instead. RPA Manager supports using connected apps to connect to Anypoint platform, which provide more secure and improved authentication mechanism than API keys. RPA Manager supports deleting users who have assigned processes and reassigning those processes to other teams. For non-federated, MuleSoft automatically creates teams in Anypoint platform to match the existing roles and user groups in RPA Manager. Teams names are restricted to alphanumeric characters, hyphens, underscores, and spaces. If your role or user group contains unsupported characters, these characters are omitted from when creating the new team name. roles migrate to teams using the following naming convention: RPA role dash existing role name. User group, these new teams have the same Anypoint permission for RPA pages that the role had in the RPA manager. User groups migrate to teams using following naming convention: RPA user group dash existing user group name. Users assigned to roles and user groups in RPA manager migrate to the corresponding team in Anypoint platform. Now we are considering choosing a hosting option in Anypoint platform hosting overview. Anypoint platform is designed to enable the control plane and runtime plane to be hosted independently. Depending on your requirements, you can choose from the following: use Anypoint platform in MuleSoft manage control plane and runtime plane. Host and manage runtime plane with your own infrastructure while connecting it with the MuleSoft manage control plane. Host both the control plane and runtime plane locally with your infrastructure. See the control plane and runtime plane support metrics in the documentation for more about running which runtime plane hosting options are supported in each control panel option. Now we are considering why we deployed on Cloud Hub 2.0 in Cloud Hub 2.0. Cloud Hub 2.0 provides for deployments across 12 regions globally. Dynamically displays the infrastructure and built-in services up or down to support elastic transaction volumes. Built-in security policies protecting your services and sensitive data with encrypted secrets, firewall controls, and restricted shell access. Encrypts certificates, password, and other sensitive configuration data at the rest and transit with Anypoint platform. Provide a standardized isolation boundary by running each Mule instance and service as a separate container. For Cloud Hub 2.0, pricing information, contact either your account executive or your account deployment representative. Now we're considering August 25, 2023 Cloud Hub 2.0 release notes. What's new? When you attempt to delete a private space that has apps deployed, the warning appeared confirming you want to delete the private space and the apps that are deployed to it. If you continue to deletion, private space and all its deployed apps are deleted. Now we are considering technical enhancement from the Cloud Hub 1.0 to 2.0 in Cloud Hub 2.0 for Cloud Hub 1.0 users in features of Cloud Hub 2.0. The following improvements have been made to features that are also available in Cloud Hub 1.0. With the added functional vCore offerings in Cloud Hub 2.0, you may no longer need to bundle multiple listeners in the same application to reduce your resource usage. In Cloud Hub 2.0, private access functions has improved VPC from Cloud Hub 1.0. You can automatically assign private network from the application in private space. You can also configure private ingress load balancer that auto scales to accommodate traffic. By default, VPNs allow high availability. Applications now have public and private endpoints. By default, you can also configure multiple public endpoints. You can access the endpoints addresses in Runtime Manager. You can make namespace edits and updates to the TLS context and infrastructure of ingress layer. In Cloud Hub 1.0, application names had to be unique per control panel plane. In Cloud Hub 2.0, application names must be unique per private space. Custom log4j.xml is supported by default to enable streaming logs to external log collectors. You no longer need to contact support to enable or disable this feature. You can disable log streaming using Runtime Manager. You no longer need to contact support to enable or disable this feature. Self-service logs for dedicated load balancer and ingress are available via the private space. Titanium users can also download logs through Anypoint monitoring. Users using ports 80 and 443 applications inside the private space can communicate using internal load balancer via the private endpoint. This depends on application protocol. Now we are considering update the runtime version manually in monthly date patch updates in Cloud Hub 2.0 operating system patch updates in Cloud Hub 2.0 architecture. Login to Anypoint platform, navigate to the runtime manager. In the runtime manager navigation menu, click applications, select the application you want to update. In settings, in the deployment target tab, click the runtime version drop down, select the latest build for your version, click deploy. The application redeploys with the new runtime version. Now we are considering creating a private space. Create a private space. In creating private spaces in extending your network to Anypoint platform with private spaces in Cloud Hub 2.0. From Anypoint platform, select runtime manager, then private spaces. The page shows any private spaces shown with the selected business group. Click create private space. Enter the name for your private space and click create. You cannot rename your private space after you created it. Now we are considering deploy an app to a shared space. In deploying apps to shared space, in deploying apps to Cloud Hub 2.0. From Anypoint platform, select runtime manager, then applications. Click deploy application. Then on the deploy application page, enter the name of the application. Important, you cannot change the name of the app after you deploy it. You change the name, and the name you must delete and redeploy the app using new name. Then select an application file. To upload the Mule jar file from your system, choose file and then upload file. Choose an example app from Anypoint Exchange. Select choose, then import file from Exchange. Then you get in the get from Exchange page, enter hello in the search assets by name. Click the hello world and then click select. Then they select Cloud Hub 2.0. Then the shared space for the region from the deployment target list. For the list of regions, select shared global regions. See the shared global regions in the documentation. If you have global deployment entitlement, all regions are available. If you have a region restriction based on the subscription, only regions that are available to your organization appear. Configure options for the deployment. Specify runtime options. Change app behavior with properties. Configure logging for the app. Then click deploy application. Now we are considering update app settings in updating the apps deployed to the Cloud Hub 2.0 and managing apps deployed to Cloud Hub 2.0. From Anypoint platform, select runtime manager, then applications. Then click runtime. Click the app name. Click in the navigation name. Click settings. Click configuration to display the app configuration history. Config tab, changes tab, display the changes to successfully deployed application configuration, and includes the last 10 configuration deployments in order by configuration date. A unique hash identifies each configuration in the history. All changes tab display the history of versions created from the configuration deployment and the actions performed on each version. 5. Here depending on the deployment target, shared or private space, change the deployed configuration. Specify the name runtime options that such as uploading new application file or changing the deployment target and resource allocation. View the app's current version. Change the public endpoint for the app. Change the app behavior with properties. Disable or enable the app logs and specify log event levels. Click apply changes. The message appears at the top of the page indicating the configuration is on progress. Click view status to view the status for each replica in the deployment. When the configuration is successfully applied to the deployed, a message appears in the top of the page, and with the application status, configuration identified, date and replica status. New configuration appears in the config changes list. In the configuration updates fail to deploy, the message indicates that the Cloud Hub 2.0 didn't apply the configuration. Configuration status is update failed, and the configuration appears in the config changes history without a label. In failure cases, the deployment attempts to roll back to the last successful version of configuration. In some situations, the rollback might not succeed and the configuration status is update failed. Now we are considering view logs in viewing log data for deployed apps in monitoring apps deployed to Cloud Hub. To view logs for applications deployed into a private space, from Anypoint platform, select runtime manager, then applications. Click the app name. In the navigation menu, click logs. The logs page displays all logs for replicas for the selected config with the latest messages at the bottom. The config represents the deployment since the last update. When you update application, new configuration is created. In this case, the logs page might be empty. The page stream logs messages as they occur unless the last deployed action is closed. Log from the before and last updated time appear in the drop-down containing previous deployment. Each message includes the severity, time relative to relative and absolute, and replica name. To view logs for different config, click the config drop-down list and select the config. Config label indicates the relative time of deployment, such as 10 hours ago. Now we are considering enable the monitoring agent in Cloud Hub setup in Visualizer. In order for your app to appear in Anypoint Visualizer for metrics to be displayed, you must manually enable the Anypoint monitoring agent for the following Mule versions. Mule version 3.8.7 patch releases available after August 14, 2019. Mule version 3.9 patch releases available after April 5, 2019. Mule version 4.1 patch releases are available after March 22, 2019. Mule version 4.2. To enable the Anypoint monitoring agent, log into Anypoint platform using the account that has the Anypoint monitoring permission. Navigation bar or main Anypoint platform screen, click monitoring. In the Anypoint monitoring navigation menu, click settings, select Cloud Hub. From the environment drop down list, choose environment. In the list of resources in the environment name, search for the app to visualize. Next to the app, click enable and apply to enable visualization and monitoring for the app. Now we are considering CLI for Cloud Hub applications. In Cloud Hub in Anypoint CLI, runtime mg Cloud Hub alert list. This command lists all assets associated with your current environment. This command has the -- output flag. Use the output flag to specify the response format. Support values are table, default, and JSON. This command also accepts the default flag -- help. Now we are considering CLI for Cloud Hub dedicated load balancers in Cloud Hub in Anypoint CLI. The command here the Cloud Hub : balancer list. This command lists all the load balancers in your Anypoint platform. It displays the load balancer's name, domain, its state, and the Anypoint VPC ID to which the load balancer is bound. This command has the -- output flag. Use -- output flag to specify the response format. Support values are table, default, and JSON. This command also accepts the default flag -- help. Now we are considering CLI for Anypoint virtual private cloud in Cloud Hub in Anypoint CLI. Cloud Hub : VPC : list. This command lists all the available Anypoint VPCs. It returns ID, region, and environment of the network and where it is the default Anypoint VPC or not. This command has -- output flag. Use the -- output flag to specify the response format. Supported values are table, default, and JSON. Now we are considering deploy an app to Cloud Hub. In deploying Mule apps to Cloud Hub, we are developing integrations in Anypoint Code Builder. When you deploy an application to Cloud Hub, Anypoint Code Builder configure the default deploy.json file in your source main resources directory. If you need to configure the properties at deployment time, for example, create SQL properties, Anypoint Code Builder prompts you to modify the deploy.json during the deployment process. To deploy your app to Cloud Hub, in the activity bar of the IDE, click the Mule Anypoint Code Builder icon. To the open the configuration XML file for the Mule app. To deploy, click the deploy to Cloud Hub icon. Alternatively, open the command palette and select MuleSoft : deploy to Cloud Hub. For the if prompted, click allow to sign in the using Anypoint platform and select the business group. If the project doesn't already have deploy.json file, Anypoint code builder prompt that deploying configuration file has created and opens it from it for you to review. For example, the application name property define the part of URL that you use to access your application on the Cloud Hub. This name must be unique across all applications deployed to Cloud Hub. After reviewing the deployment configuration, click deploy to deploy the application to the Cloud Hub. At the prompt, select the environment to deploy. At the prompt, then Anypoint code builder packages the application and deploys it to the Cloud Hub. The output panel opens the Mule Maven output. After deployment is complete, click open in Runtime Manager. Your app opens in the Runtime Manager in Anypoint platform. The domain name of the application varies, but it follows the similar structure, such as app with 40 schedulers episode for schedulers.us w1.cloudhub.io. Open the preset preferred REST client and make the get request to your domain name as displayed in the runtime manager. For example, http:// app with 100 schedulers.us w1.cloudhub.io/API/flights. Now we are considering configuring OAuth 2.0 connectors on Cloud Hub. You can deploy your OAuth 2.0 enabled connectors to the Cloud Use Service. Configuring OAuth 2.0 for connector on the Cloud Hub is the same as the configuring OAuth 2.0 for the connector locally, except for Cloud Hub. The Mule application is behind an extra server. Consider the following when configuring OAuth 2.0 for the connector on the Cloud Hub. Connector listener. Cloud Hub manages the some properties for you automatically, such as http.port and http.port. These properties when configuring your HTTP listener. When deploying on the cloud, the localhost 0.0.0.0 and 127.0.0.1 hosts are no longer publicly reachable. When configuring your OAuth provider, you must replace all links contained in those hosts with actual Cloud Hub provided public addresses. For Cloud Hub, this address is in the format chname appname.region.cloudhub.io. For example, HTTP appname ch example app deployed in the Europe London region has public address http:// ch example app.uk.e1.cloudhub.io. OAuth provider setup. If you set callback path to /callback, your public callback URL is chappname.region.cloudhub.io /callback. This is the callback URL to use as your direct URI when you configure your OAuth provider. Logging, signing direct URLs. Allow wildcard in logging URI direct. This must be configured to your connector as the external callback URI. You can use full domain property that Cloud Hub configured for you to automatically obtain the property hostname. If you are deploying to multiple regions or have some other gateway configured, use your hostname of the load balancer or the gateway in your OAuth provider callback URL and external callback URI. In the OAuth 2.0 configuration, user not OAuth provider reaches the callback endpoint from the browser. Ensure that your region is configured correctly and you create a Cloud Hub app in the US region and users connect to the app from the Europe. Request is blocked by the gateway. Now we are considering enable monitoring on Cloud Hub Cloud Hub important Cloud Hub settings in configure and enable Anypoint monitoring for Mule apps in Cloud Hub and in monitoring. You can enable monitoring for your Cloud Hub apps on the supported versions of Mule by adding a property to an application deployed to Cloud Hub. Log into the Anypoint platform. In the navigation bar or the main app, Anypoint platform screen, click Runtime Manager. And in the list of applications, select the application for which you wish to enable monitoring. In the application must be deployed to Cloud Hub and running on the supported version of Mule. In the navigation menu, click settings. In the properties, and add the following property: anypoint.platform.config.analytic.agent.enable equal true. To disable monitoring, change the value to false. Click apply changes. Now we are considering WebSockets connector in Cloud Hub version 4 in WebSocket connector in connectors. If you have you can deploy Mule apps that contain inbound WebSockets endpoints and outbound WebSocket endpoints, so both to Cloud Hub. If your app has inbound WebSockets endpoints only, to deploy the app in the Cloud Hub, you must configure an Anypoint virtual private cloud VPC. Set up the dedicated load balancer to route WS and WSS traffic through the Mule app. Now we are considering deploy to Cloud Hub. In deploy a Mule application to Cloud Hub in Studio, right click the project folder on your package explorer view, select the Anypoint platform and then deploy to Cloud Hub. If you don't have your Anypoint platform credentials configured into Anypoint Studio, you will need to provide your login information before to continue. Configure to Cloud Hub instance to which your application is being deployed. Now we are considering deploy an application to Cloud Hub EU control panel in EU plane. The procedures for deploying an application to Cloud Hub in EU control plane is similar to those in the US control panel. However, consider the following the differences when deploying to EU control panel. EU control panel supports a smaller number of Mule runtimes than the US control panel. The domain of the Cloud Hub workers is appname.de.eu1.cloudhub.io. You can only deploy to Frankfurt and Dublin regions from the EU control panel. Application deployed in the EU control plane use object store version 2. Now we are considering deploy API to Cloud Hub. In step 5, we deploy the API to Cloud Hub in built an API from start to finish. To deploy an API in the form of Mule app from the studio, in the Mule design perspective, right click the Hello World app project in for example in your Explorer, package Explorer, and then select Anypoint platform, then deploy to Cloud Hub. If prompted, enter the Anypoint platform username and password and click sign in. You must be in your account sandbox. You must be in your account sandbox to deploy the API. If you see the design instead of sandbox, click the design to launch the switch environment dialog and click sandbox, then click switch. In the deployment application, enter the deployment application, enter the hello world greeting, first name, last name. Every app and API name must be unique across the Cloud Hub. This example uses hello world greeting Sandy Kim. For the deployment target, select Cloud Hub. Don't change any of the other default values. Click the deploy application. After a brief pause, Windows displays the status of the deployment. Click open in browsers to see the status displays in the on the in runtime manager. When the project is successfully deployed, runtime manager display the status started. To test the API deployment, send the request from advanced REST client. Click started to display the app URL. Copy the app URL, which this in this case the hello world greeting.sandykim.use2.cloudhub.io plus this URL is also be used later when configure the proxy API plus. In advanced REST client, send the request to the base URI that you just copied. Be sure to add the API endpoint /API/greeting. And if you get the 200 OK, then the greeting you specified today is greeting hello, for example, and then you can have successfully deployed the API you created. Now you need to create API proxy application for this API to restrict access and keep service protected. You will add a rate limited policy, which you can do while the API is running, for example. Now we are considering steps to follow in runtime manager in deploy a Mule application from runtime manager to Cloud Hub by using a Java file. In deploy a Mule application in flow design in design center. Switch to the Cloud Hub environment in which you want to deploy the app. Click the deploy application. On the deploy application page, select file, upload file, then upload file and upload the Java file. Follow the instruction in deploying to Cloud Hub. Now we are considering CLI for Cloud Hub 2.0 in Anypoint CLI. Here the runtime dash manager application, runtime dash manager colon application colon delete deletes the running application is specified in the app ID. To get this ID, run the runtime dash manager mgr application list command. Warning: this command does not prompt twice before deleting. If you send a delete instruction, it does not ask for confirmation. This command accepts only the default tag dash help. Now we are considering create notification in Cloud Hub connector 1.1 reference mule 4. Cloud Hub colon create dash notification creates a new notification. Now we are considering deploy application to Cloud Hub using the Mule Maven plugin. In deploy Mule applications in Mule runtime. Inside the plugin element in your project's pom.xml file, configure your Cloud Hub deployment, replacing the placeholder values with your Cloud Hub information here. With the command maven clean deploy dash d mule deploy here. Now we're considering configure the Cloud Hub 2.0. Here the deploy applications to Cloud Hub 2.0 using the Mule Maven plugin. In deploy Mule application in Mule runtime, here the Maven MVN clean deploy dash d Mule deploy. As an exception example, we can consider this one. This is occurred during our API call curl -x get /https any / anypoint.mulesoft.com /cloudhub /api /applications /supported mule versions here -h authorization bearer and with then 16e6 etc. The root exception is stack trace com.mulesoft.cloudhub.client cloud hub exception forbidden at etc. As an example 2, we can consider this error while deploying the project: unable to create plugin from class com.mulesoft.muleesb.datamapper.plugin.datamapper plugin org.mule.api.lifecycle.initialization exception. And etc. As an error example, we can consider this error occurred in the environment with Anypoint Studio. Deploy to Cloud Hub application deploy has failed. Recent application deploy has failed. As an error example 2, we can consider this build failure in the environment with Anypoint Studio 5.2.0 and Mule ESB 3.0. 3.70. Warning: the POM for COM46 MuleSoft 46 Mule ESB colon Mule core EE jar is missing, no dependency information available. Warning: the POM for COM etc. the modules colon Mule module spring config jar is missing, no dependency information available etc. Here this we can consider as an error example 3. We can consider this code segment. Expect an error in your test. The key is taken from the payload. And if the key is null, the object store connector will throw an error with OS colon invalid key error type here. To the test to validate this case would be something like this here. The here the Anypoint 2.3. The Anypoint is a Mule application testing framework that allows you to easily build automated tests for your integrations and APIs. It provides a full suite of integration and test unit capabilities and fully integrated with Maven Surefire for integration with your continuous deployment environment.